A single star pours out more light in 1 second than our whole civilization has made in all its history, and the space right beside it stays perfectly black. On clear nights, the brightest stars burn through the dark, sharp and steady, while the gaps between them hold nothing at all. Yet, if the universe is filled with stars in every direction, the sky should be a solid wall of light, bright as the face of the sun, with no room left for dark. Why is space so dark when the stars inside it are so bright? The darkness between the stars is not something that begins at sunset. It is above us right now, even at noon, while the ground is filled with sunlight. Go high enough above the air, and you see what every astronaut describes the same way: the sun still burning, full power, exactly as bright as noon on a beach, and the sky around it completely black in every direction. The blue overhead at noon is not space. It is sunlight knocked sideways by the molecules in the air, the same way a flashlight beam becomes visible when you shine it through smoke. Remove that thin shell of air, and the truth is revealed. The background behind the sun was never blue. It was black all along. So when we talk about why space is dark, we are not really talking about night. Nighttime is a local shadow, your piece of ground rotating away from a nearby star for a few hours. That is a fact about a spinning planet, not about the universe. The darkness this question is after is the permanent one, the black that holds between the stars in every direction, regardless of what time it is. A darkness that is sitting 300 kilometers above your head right now, in the middle of the afternoon, and has been there since before the Earth existed. That darkness is the strange one. The universe contains an enormous number of light sources. Our galaxy holds somewhere between 200 and 400 billion stars. Think about the count for a moment. If you started naming stars out loud at 1 per second and never stopped, never slept, you would need about 10,000 years to get through only our galaxy. Then consider that the number of galaxies in the observable universe is in the same ballpark as the number of stars in our galaxy. For every star you could name in the Milky Way, there is an entire separate galaxy of stars burning somewhere else in the dark. The total runs into something like a few 100 billion trillion. A number that large stops being a number and becomes closer to a fact about the character of the universe. And the sky between all of them is black. Pick any direction from your eye and draw a line straight outward into space. In a universe with no outer wall, filled with stars at every distance, that line is trying to miss every single star it passes. But stars are not infinitely small points. They are enormous objects. Our sun alone spans about 109 Earth diameters across. In any direction you draw that line, with stars scattered through the space it crosses, the line has to keep threading between them. The farther it goes, the more of them it has to dodge. In a deep enough universe, the odds of that line making it through forever, missing everything, go to zero. The line has to land somewhere. In a universe without a boundary, it has to land on the surface of a star. Every direction you pick, the same logic applies. If every direction ends on a star, there are no directions left over to stay dark. The response is that distance takes care of it. A star twice as far is 1/4 as bright. 10 times as far, 1/100th as bright. Stars far enough away should fade below the threshold where they matter, and most sightlines should stay dark by default. This is the intuition almost everyone lands on, and it turns out to be wrong in a way that has a clean explanation. Imagine a thin shell of space at some fixed distance from you, filled with stars. Now push that shell out to twice the distance. Each star in it is now 4 times farther away, so each one delivers 1/16th the light. But a shell at twice the distance wraps around a sphere with 4 times the surface area, so it holds roughly 4 times as many stars. 4 times the stars, each at 1/16th the brightness, and the total light from the outer shell is exactly the same as from the inner one. Every shell of the universe contributes an equal amount of brightness to your sky, no matter how far out it sits. In a universe without an edge, those equal contributions keep adding up outward forever, without stopping. Distance was supposed to be the escape. The geometry of shells closes it off. Follow that where it leads. In a universe infinite in extent and old enough for all that accumulated light to have made the journey here, every single point of the sky should shine with the full brightness of a star's surface. The whole dome overhead, blazing with the intensity of looking directly at the sun from every direction simultaneously, with no part of the sky left to be anything else. And now think about what that means physically. Earth's temperature is set in rough balance by a single star, delivering energy from one direction. A sky glowing at full stellar intensity from all directions at once would not just be blinding, it would push every surface on the ground toward thermal equilibrium with a star's surface temperature, which typically runs several thousand degrees. At several thousand degrees, liquid water is gone. The chemistry that builds living things cannot hold together. The darkness you are in right now is not just comfortable. It is one of the physical conditions that allowed anything alive enough to ask this question to be here at all. There is something underneath this that does not come up in most explanations of the problem. The dark corridors between stars are not empty of light. Right now, beams from thousands of different stars are streaming through every cubic centimeter of that space, crossing in all directions at once, passing straight through each other without interacting. A beam from Andromeda and a beam from a star on the far side of our galaxy can cross the same point in space at the same moment, and neither one is affected by the other. The space between any two stars you can see is already saturated with light and motion. None of it shows up to you because of something precise about how vision works. A beam of light only registers when it ends in your eye. A beam crossing the gap at an angle, aimed at some other destination entirely, moves right through your field of view without leaving any trace. Darkness in a given direction does not mean the light is absent from that region. It means no beam in that region was sent, from any source, along a path that terminates at your retina. The gap between two stars looks dark not because nothing is happening there, but because none of what is happening there was addressed to you. The question was never about where the light went. The question is about why so many lines from your eye reach outward into this universe packed with stars and arrive at the far end without finding one pointed back at you, sending something back. Johannes Kepler worked through the geometry in 1610 and came away with a conclusion. A universe infinite in stars produces a bright sky. The sky is not bright, so the stars do not go on forever. He was wrong about what the darkness proved, but right about what it was, a measurement, a constraint, something the universe was telling him. Thomas Digges had already placed stars through an infinite three-dimensional space in 1576 and noted almost in passing that such a universe should be brilliant in every direction, then moved on without stopping to ask why it was not. He had the entire problem in one sentence and walked past it. The night sky held its secret for another 250 years after that, until the tools existed to understand what kind of universe could be dark at all. 3 answers have been put forward at different points in that history. The first involves dust between the stars absorbing the light from distant suns before it can reach us. It sounds plausible until you work through what thermodynamics says about a dust cloud soaking up light forever. The second involves the stars simply running out at some distance, leaving the far sight lines empty. It moves the question without answering it. And the third involves time, the age of the universe, light that has not yet had long enough to complete its journey here. That one is closest to the truth, but not quite there. And the gap between almost right and exactly right is where the real story is. What would the sky look like if the universe had no age limit, no outer edge, and all that geometry had infinite time to pay out? Stand deep enough in a dense forest and look in any horizontal direction. Bark. Not eventually. Not after searching through gaps. Within a few meters, your line of sight lands on a tree trunk. The forest does not need to be infinite to produce this, only dense and deep enough that no sightline can thread between every trunk and reach open air beyond. Now extend the forest without limit in every direction, the same density maintained forever. Every horizontal line from your eye is guaranteed to end on wood. No direction is left over to look out through. What changed is not the density. What changed is that there is no longer any edge to reach, no point where the trees run out and the corridor between two trunks finally opens onto a clearing. The enclosed feeling of standing inside it is not a mood. It is the logical consequence of a forest with no boundary. In that forest, one escape still exists. Tilt your head back. Above the canopy, however thick it is, gaps appear between the branches, and beyond them, open sky. The forest surrounds you horizontally, but not in 3 dimensions. In a universe filled with stars, that rescue does not work. Every direction from your eye is a potential sightline through space. The corridor between 2 stars that looks dark is the forest path between 2 trunks, where the next one is simply farther down the line. The darkness at the end of that corridor is not open space beyond the stars. It is the approach to the next star, the one your line of sight has not yet reached. The star that closes the sightline may be 1,000,000 light years away or 1,000,000,000, but in an infinite universe, it is there. 2 conditions are required for this to hold at its full force. The universe must extend without limit in space, so that no direction runs out of stars before the sightline closes, and it must have existed without limit in time, so that the light from every star at every distance has had long enough to arrive. These 2 requirements work differently, and it matters which one is missing. A universe infinite in space but young in age still gives light a way out. A star 100 billion light-years away, in a universe only 14 billion years old, has been sending its light toward you since it formed. But that light is still in transit. The photons exist. They are on the way. The sightline to that star is not dark because the star is missing. It is dark because the message has not arrived yet. A universe with no starting point, one that has been running forever in every direction, eliminates that delay entirely. Every photon from every distance has had infinite time to complete its journey. An eternal universe of stars has no mechanism left for leaving any part of the sky dark. Before the middle of the last century, these 2 conditions were not exotic assumptions. They were the default. A universe with a spatial edge raised a question no one had a good answer to, which was what lay on the other side of the edge, and why the edge was where it was rather than somewhere else. A universe with a beginning raised questions about what existed before the beginning and what caused it to start. Questions that sat at the boundary between physics and matter's physics had no tools to address. An infinite, eternal universe was not a leap of faith. It was what you believed if you tried to follow the evidence as far as it went and avoided adding assumptions the data did not require. The dark sky was sitting in plain view the whole time, contradicting it, and it went unquestioned because it looked like the natural backdrop rather than a piece of information. The surface of our sun emits roughly 2 billion watts for every square meter of its area. That is the source of the squint, the sunburn, the need for shade, the reason direct eye contact with it is damaging within seconds. In a sky where every sightline terminates on the surface of some star, every point of the sky delivers that same surface brightness. The full moon on a clear night, bright enough to read by in open fields and to cast a faint shadow of your hand, delivers about 1/400,000th of the light of direct sun. An Olbers bright sky is not a sky with 400,000 moons in it. It is the entire celestial sphere glowing uniformly at the intensity of the sun's face, in every direction at once, with no corner of the sky left at a softer level. The scale of the difference between that and what you see when you look up is one of the more striking mismatches between what the universe seems obligated to produce and what it delivers. Earth's surface temperature is held in rough balance by a single star delivering energy from one direction across one hemisphere. Change that to every direction simultaneously, with every point of sky radiating at the intensity of a stellar surface, and the balance point of the calculation shifts catastrophically. The equilibrium temperature of any exposed surface under those conditions would rise toward the temperature of the stellar surfaces doing the radiating. For stars like our Sun, that temperature runs around 5,000 to 6,000 degrees on the absolute scale, the scale that begins at the coldest anything can be. Iron boils at roughly 3,000 degrees on that scale. Rock vaporizes somewhere below 6,000. At those temperatures, there is no ground to stand on, no air to breathe, no liquid water to sustain any chemistry complex enough to call it life. The darkness overhead is not an absence. It is the one condition under which any of the organized structure in this universe has the thermal breathing room to exist. A paradox is not a question with an answer that is hard to find. It is a structure in which two claims that both appear solid are in direct contradiction, and neither one can be easily abandoned. The night sky is dark. That is observable fact, as certain as anything gets. A universe that is infinite in extent and age, with stars spread uniformly through it, produces a bright sky. That is a conclusion of geometry, and the geometry is airtight. Both cannot be true. Yet every premise in the chain was, for most of scientific history, the least assumption position available. The paradox does not accuse anyone of carelessness. It built itself out of the most reasonable beliefs of its era and waited. Edmund Halley, whose name the famous comet carries, worked through the problem in 1720 and concluded that an infinite universe would deliver infinite brightness to every point in space, which clearly did not match the sky above him. Jean-Philippe Loys de Chezeaux reached the same conclusion in 1744 and proposed that matter between the stars must be absorbing the light from distant sources before it arrived. Heinrich Wilhelm Olbers restated the paradox in 1823, reached the same conclusion about absorbing matter, and the name attached to both him and the problem in a way that held. None of them were wrong about the paradox itself. The geometry they described was correct, the solution each of them proposed was not, and the specific way it fails opens a door that matters more than the failure itself. Three assumptions carry the paradox. The universe has no spatial limit. It has no limit in time. Stars fill it without significant thinning across the distances involved. Pull any one of those and the sky is permitted to be dark. Dust between the stars was a proposal to keep all three intact by adding a fourth mechanism, something to intercept the light before it finished its journey. What happens to that dust, if you let the physics run forward, is the place where the paradox stops being a historical curiosity and starts becoming a lesson in how the universe handles its energy. For most of human history, the darkness between the stars required no explanation because it could not be a paradox. The universe that dominated Western astronomical thinking for roughly 2,000 years placed the stars on a single sphere, the outermost layer of a finite nested system with Earth at the center. Stars were not scattered at varying distances through open space. They were lights fixed to the inside surface of a dome. In that cosmology, the geometry of Olbers' paradox could not arise. A dome has a finite number of lights, each at a fixed distance. Between the lights, the surface of the dome itself serves as the background. The sky is dark between the stars for the same reason a ceiling is dark between its lamps. The background is simply unlit material, not an open line of sight running to infinity. The question of why sightlines fail to hit stars does not form, because sightlines end at the dome. Nicolaus Copernicus displaced Earth from the center in 1543, but he kept the outer sphere. His universe was heliocentric and far larger than the Ptolemaic one, but the stars still occupied a fixed shell at the boundary. The paradox still could not arise. An outer shell of stars, however far away, is a dome. Sight lines between the stars still terminate at the shell itself. The change that made the paradox possible came 33 years later from an English mathematician and astronomer named Thomas Digges. In an appendix he added to his father's almanac in 1576, Digges took the Copernican model and broke the outermost sphere open. He did not merely enlarge it, he removed it. In his diagram, stars scattered outward in every direction without any enclosing boundary, annotated with the phrase describing the fixed orb of the stars as infinitely extended in altitude. The stars were no longer on a surface. They were distributed through an infinite volume of space. Digges was religious about this. He described the infinite star field as the dwelling place of the elect, God's angels at infinite distances, the cosmos as a theological statement about the unboundedness of the divine. The infinity was not alarming to him. It was confirmation. What he did not do was follow the geometry through. Stars at infinite distances through infinite space means that every line of sight, extended far enough, must end on one. He noted that distant stars appeared faint and difficult to see, which is true of any individual star at great distance, and seems to have left it at that. The shell argument, which shows that faintness of individual stars is exactly cancelled by their increasing number at greater distances, was available in principle to anyone thinking carefully about it. Digges built the universe in which it applied and walked straight past it. Giordano Bruno did not walk past anything. Bruno, an Italian philosopher and ex-friar, who had cut his way through several countries and several religious orders by the time he arrived at his cosmological views, argued in the 1580s and 90s for an infinite universe filled with an infinite number of suns, each one potentially circled by worlds, with no center and no edge anywhere. This was not a cautious extrapolation from Copernicus. Bruno said explicitly that our sun was one star among an infinite number, that the idea of a special central position for any object in the cosmos was a relic of a smaller and more self-important understanding. He lectured on this in England, France, Germany, and Italy. He published books arguing it. He made enemies with fluency and thoroughness. The Inquisition arrested him in 1593. His trial ran for 7 years. He refused to recant. In February of 1600, he was burned at the stake in the Campo de' Fiori in Rome. The charge sheet against Bruno mixed cosmological claims with theological ones, and historians still debate the precise weight of each in the final sentence. What is not debated is that advocating for an infinite universe populated with other suns was, in that period, not a neutral philosophical position. Bruno's execution did not prove the position wrong. It demonstrated what kind of attention it attracted. Anyone who engaged the infinite universe seriously in the years immediately after 1600 did so in the shadow of what had happened to its most prominent defender. The books Bruno published in the 1580s made explicit what his trial would later render politically dangerous. In On the Infinite Universe and Worlds, published in 1584, he argued that each star in the sky was itself a sun, surrounded by its own system with the potential for inhabited worlds around it. He took the Copernican revolution and extended it past where Copernicus had been willing to go. Copernicus displaced Earth from the center. Bruno removed the center entirely. In an infinite universe with stars in every direction, there is no privileged point, no axis around which the rest rotates, no location that can call itself the middle of everything. The darkness between the stars did not appear as a problem in Bruno's writing. He was arguing for the existence of other worlds and other suns, not working through the geometric consequences of how much light they would collectively deliver. The paradox sat inside his cosmology without being addressed. Johannes Kepler engaged it anyway, and he engaged it critically. In 1610, the same year Galileo published his telescopic observations of mountains on the moon and moons around Jupiter, Kepler wrote a response that included a sharp argument against the infinite star field Bruno had advocated. His reasoning was clean. If stars extended through space in every direction without limit, then any line of sight extended far enough must reach 1. The whole sky, from every vantage point, should glow as brightly as the surface of a star. The sky does not do that. Therefore, stars do not extend without limit. Kepler used the darkness as evidence. He took what everyone looked at every night and treated it as a measurement rather than a backdrop, a constraint on cosmological structure rather than an aesthetic feature of the universe. The logic was right. A universe infinite in space and eternal in time, filled uniformly with stars, cannot be dark. If the sky is dark, at least one of those conditions fails. Kepler identified the correct structure of the argument. Where he stopped short was in assuming which condition had to fail. He chose the spatial extent. Stars end somewhere. The visible darkness in every direction between the bright points marks the places where no star exists, where sight lines reach the edge of the populated region and stop. It was a reasonable conclusion given what was available to test. It also raised a question he did not have the tools to answer, which was what lay beyond the edge of the stars, why the edge was where it was, and what kept the stars from simply falling inward on one another over time. The pattern across these three figures is consistent enough to notice. Digges built an infinite universe and passed the brightness problem without stopping. Bruno argued fiercely for infinite stars and was killed before the paradox could become his problem. Kepler saw the paradox clearly, used it as a logical tool, and resolved it by choosing the simplest revision available, which was to say the stars end. None of them asked whether the universe might be finite in time rather than in space. None of them considered that stars might exist at infinite distances and still leave the sky dark if the cosmos had not been running long enough for the light to arrive. The eternal universe was not a conclusion anyone had argued for carefully at that point. It was a default, the shape the universe had, unless you had strong evidence to change it. The dark sky had been identified as a diagnostic tool. The diagnosis kept pointing at the wrong patient, and the correct patient, the age of the universe, was not a quantity anyone could measure or even conceive of measuring for another 300 years. What would happen if you tried to satisfy Kepler's constraint by a different route, one that kept the stars but removed the time they had been burning? Kepler's resolution looked clean on the surface. Stars occupy a finite region of space. Sightlines that extend beyond that region find nothing at the far end. The dark between bright points is not a corridor leading to a distant star, but open space beyond the edge of a limited population. If stars simply stop somewhere, the paradox dissolves without needing to change anything about the physics of light. A finite number of stars produces a sky with a finite number of bright points and darkness, everywhere in between. The argument ends there, except that Newton's physics, which was being assembled in the same general era, made the finite universe almost impossible to maintain without introducing a different and more immediate problem. A finite cluster of stars in otherwise empty space has a center of mass. Every object in the cluster gravitates toward every other. Stars on the outer edge of the cluster feel a net inward pull because the mass of the cluster sits concentrated inside their orbit. Stars in the interior regions are pulled in all directions at once, but the pull is not symmetric enough to cancel when the cluster has a defined boundary. The whole cluster tends to contract. In his letters to Richard Bentley, a theologian preparing a series of public lectures on natural philosophy, Newton spelled this out directly in 1692. He wrote that if all the matter in the universe were scattered through a finite region of space, that matter would, by gravity, tend toward the interior of the region and fall into a single mass at the center. He was not speaking of the solar system collapsing, though that was part of Bentley's question. He was speaking of the entire star-filled cosmos contracting over enough time into one enormous heap. The time scale matters. The rate at which a gravitating system collapses depends on its density. A region as dense as the sun collapses in seconds. A region as sparse as the space between stars in our galaxy takes much longer, but the direction of motion is the same. Newton could not calculate the actual timescale for cosmic collapse because he did not know the density of stars through space, but the direction was not in doubt. A finite universe of stars had a gravitational arrow pointing toward its own center. The universe had evidently not collapsed. Something had to account for that. Gravity was what pushed Newton toward the infinite universe, not philosophy, not theology. His proposed resolution was that the stars must extend without limit in every direction, with their distribution approximately uniform throughout. In that arrangement, the gravitational pull on any given star from all the stars to its left is matched by the equal pull from all the stars to its right, above, below, ahead, behind. The forces cancel. The net gravitational effect at any point in an infinite uniform star field is zero, because there is no preferred direction for matter to fall. There is no center of mass, because there is no center. This was the structure that Newton's own equations required if the stars were to avoid falling together, and the only arrangement that satisfied it was one that ran without limit through space. Newton understood that this solution was almost absurdly fragile. He said as much in the same correspondence with Bentley. An infinite uniform distribution of gravitating matter is balanced in the way that a surface balanced exactly on its edge is balanced, possible in principle, requiring that every part of the arrangement be exactly right and unstable against any deviation from perfect uniformity. Real stars are not arranged with perfect uniformity. There are denser clusters and sparser voids at every scale. Any region that is slightly denser than its surroundings pulls nearby matter toward itself. That pulls more matter in. The local density increases, which increases the gravitational pull further. The imbalance amplifies. Newton acknowledged that the infinite uniform cosmos he proposed as a stable solution was not stable against real perturbations. His answer to this was to suggest that a continued intervention was required to maintain the arrangement. He meant by this that the stability of the heavens could not be explained by physics alone, which was an honest statement about the limits of his mechanics, even if it was not a satisfying resolution. The deeper problem with Newton's infinite uniform cosmos was not just that it was unstable, it was that, even granting perfect uniformity, the gravitational logic broke down in ways Newton did not fully anticipate. The force on any given star in an infinite uniform distribution can be calculated by summing contributions from every other star in every direction. In a truly infinite symmetric distribution, that sum depends on the order in which you add it up. Different groupings produce different answers. The gravitational force at any point is not zero. It is indeterminate. The precise version of Newton's argument that he hoped would save the infinite universe turned out to be mathematically incomplete in a way that was not fully worked out until well into the 19th century. The fix came from recognizing that in a truly infinite universe, the concept of a net gravitational force at a point requires a more careful treatment than simple pairwise summation. But this refinement came long after Newton's correspondence with Bentley, and the people working through it did not have a satisfying alternative cosmology to put in its place. The infinite uniform universe remained the least bad option for most of classical physics. What this did to the dark sky problem was tighten the knot rather than loosen it. The gravitational argument made a finite star field untenable. The instability of the infinite uniform field was a mathematical embarrassment, but not an observational refutation, since the stars were clearly still there, still spread across the sky in every direction. Astronomers could live with a formally unstable infinity that had not yet collapsed in practice. What they could not easily explain was why the sky remained dark. So, the structure of the problem, after Newton, looked like this. A finite universe of stars contracts under its own gravity and eventually collapses. An infinite universe of stars, which is what stability requires, produces Olbers' bright sky. Both paths lead to a contradiction with observation. The sky is dark. The stars have not all fallen together. Something in the picture is wrong, and neither of the two most natural revisions produces a universe that matches what is observed. Newton lived with this tension without resolving it. His published work focused on the mechanics of gravitational motion and left the cosmological stability question incompletely answered. The letters to Bentley were private correspondence, not public argument. The question of why the cosmos had not collapsed, and why the sky was dark despite the stars presumably extending to infinity, remained open. The two problems were usually treated as separate issues, one for mechanics and one for optics, rather than as two symptoms of the same underlying difficulty. Treating them separately meant that neither pointed clearly toward the real answer. One option remained that neither Kepler nor Newton had fully explored. Accept the infinite universe. Accept that sightlines in every direction terminate on a star, but propose that something intervenes between the source and the observer, that the universe between the stars is not as transparent as it appears, and that light from the most distant stars is absorbed or scattered before it completes its journey. This would reconcile an infinite star field with a dark sky without touching the gravitational argument at all. The stars could extend forever. The light from the distant ones simply never arrives. The substance and texture of what would have to fill the space between the stars and whether it could perform this function without creating its own problems was the next place the argument had to go. And the person whose name most thoroughly attached to that proposed curtain was the same one the paradox itself is named after. If the darkness is a curtain rather than an absence, what is the curtain made of? And what does the physics say about a curtain that absorbs starlight forever without limit? Cover your eyes with your hand and a bright room goes dark. The hand does not destroy the light, it intercepts it. The photons hit the surface of your palm, are absorbed into the tissue, and warm it slightly. Behind the hand, your eye receives nothing. The principle is so basic it requires no explanation. Any material placed between a source and an observer cuts off some portion of the light. More material cuts off more. Enough material cuts off all of it. Scaled up to the dimensions of the universe, this is the argument Olbers proposed in 1823, and it is the argument that de Chazot had independently proposed 79 years earlier in 1744. Two astronomers, working without knowledge of each other's conclusions, arrived at the same solution. That alone gave it the appearance of inevitability. The specific proposal was that interstellar space is not empty. Between the stars, distributed through the vast corridors that look like empty dark, there exists a thin medium of dust and gas. Light from distant stars must pass through this medium to reach us. The farther a star sits, the more of this medium its light must traverse. At some threshold distance, the accumulated material becomes thick enough that the light is completely absorbed and never completes its journey. Stars beyond that threshold contribute nothing to the sky. The shell argument that makes the paradox inescapable relies on every shell, near or far, delivering its equal contribution to the sky's total brightness. Absorption breaks this. Each successive shell's contribution is multiplied by an attenuation factor, a number less than 1 representing how much light survives the transit through the intervening medium. Stack enough shells, and the attenuation factor for the outermost ones approaches 0. The sum of contributions from all shells, instead of growing without limit, converges to a finite value. The sky stays dark, the mathematical structure works. This is what made the solution so compelling. It did not require changing anything about how many stars existed, how they were distributed, or how long the universe had been running. It required only accepting the existence of material between the stars. And that material is not hypothetical. It is there, and its effects on starlight are measurable and well documented. Turn a telescope toward the densest part of the Milky Way, the band of light that arches across the sky on dark nights, and you find something unexpected inside it. Patches of blackness, not fainter regions where fewer stars happen to sit, but voids in the star field where no stars appear at all. These dark patches were catalogued in detail by Edward Emerson Barnard in the early decades of the 20th century, and his list runs to hundreds of objects. Each one is a cloud of dust and gas so dense that the stars behind it are invisible. The light from those stars is absorbed before it reaches us. The dust is not metaphorical. Walk into one of those clouds, and the starlight behind you would vanish as completely as a lamp seen through a closed door. The shielding capacity of concentrated interstellar matter is a physical fact directly observable in the dark rifts that split the Milky Way whenever the air is clear enough and the sky is dark enough. What interstellar dust is made of took most of the 20th century to establish. The particles are small, typically much smaller than a grain of sand, most of them in the range of a fraction of a micrometer across. Their composition is primarily silicates and carbon compounds, with some fraction of frozen molecules coating the surfaces of the grains. They absorb light across a broad range of wavelengths, but they absorb short wavelengths, blue and ultraviolet, more efficiently than long wavelengths, red and infrared. A consequence of this selectivity is that stars viewed through intervening dust appear redder than they should. Their blue light is removed, and the red survives the transit better. This reddening is detectable with instruments sensitive enough to compare a star's observed color with the color its temperature predicts it should have. By the middle of the 20th century, interstellar reddening had been measured toward hundreds of stars, confirming that the medium Olbers had proposed was real and that it was affecting light across large distances in exactly the way an absorbing medium should. The intellectual sequence between de Chezaux and Olbers runs in an unusual direction. In 1744, de Chezaux wrote that if the stars extended to infinity, but the sky remained dark, the only resolution he could find was that space contained a fluid capable of extinguishing light. He framed it cautiously, as a mathematical necessity rather than a confident physical claim. Olbers in 1823 was more direct. He proposed that an absorbing medium was not merely a hypothetical out, but the actual explanation for the dark sky, and he tied it to the same medium that was visibly affecting the appearance of stars observed through the plane of the Milky Way. The argument was coherent. The medium was real. The mathematics worked. For roughly a century, this was an acceptable place to leave the paradox. Not solved in a rigorous sense, but contained. What made the absorption answer difficult to test and therefore difficult to dislodge was that the proposed medium, if sufficiently fine and evenly distributed rather than clumped into visible clouds, would be nearly impossible to detect directly. A uniform haze thin enough to be transparent over short distances but opaque over cosmic ones would not produce visible dark patches. It would simply dim and redden all distant sources equally, which is an effect that requires knowing the intrinsic brightness of each source before you could measure it against the observed brightness. The test for whether an absorbing medium was responsible for the dark sky would have required tools that did not exist in Olbers' time and were only developed in the 20th century. There was, however, a physical constraint sitting inside the absorption argument that did not require new instruments to notice. It required thermodynamics. Any material that absorbs radiation accumulates energy. The energy goes somewhere. In the case of dust, it goes into heat. A dust grain that absorbs a photon from a star is fractionally warmer afterward. If it absorbs another photon from another star before it has had time to cool, it is warmer still. In the universe, the absorption argument describes, with an infinite number of stars sending light toward every point in space, the rate of energy arriving at any dust grain is finite but continuous. The grain absorbs, warms, and then re-radiates that energy as thermal emission. The temperature at which it stabilizes is the temperature at which the rate of emission equals the rate of absorption. In a universe where the sky would otherwise be as bright as a star's surface, the equilibrium temperature of the dust reaches the same value as the stellar surfaces providing the light. At that point, the dust is not dark, it glows. A curtain that intercepts light forever and keeps it from reaching the observer works as long as the curtain stays cold. A curtain soaking up energy from an infinite star field does not stay cold. It heats until it radiates as much as it receives. At the point of equilibrium, the curtain is emitting light at the same rate the stars behind it would have. The observer behind the curtain sees not the stars but the curtain, and the curtain is just as bright as the stars would have been. The absorption solution does not make the sky dark. It replaces one source of brightness with another source of identical brightness and leaves the paradox entirely intact. What the thermodynamics requires, step by step, to show exactly why the curtain cannot remain cool enough to perform the function Olbers assigned to it. Place an iron skillet on a burner and hold your hand near it, palm down, close enough to feel the heat rising from the metal. Give it 10 minutes. The skillet absorbs energy from the gas flame, converts it to heat, and the temperature rises. Now remove the flame and replace it with a much brighter one, 10 times hotter, and leave it running indefinitely. The skillet cannot absorb without limit. At some temperature, it begins to glow. First a dim red you might barely catch in a dark kitchen, then a brighter red, then orange. If you push the temperature high enough, which requires more energy than a kitchen burner can supply, the skillet would eventually glow white, radiating light at every wavelength across the visible spectrum. The skillet did not create this light from nothing. It converted incoming energy into outgoing radiation, and the temperature at which it stabilized was the temperature at which these two rates balanced. This is the physics that ends the dust solution. Every object above the coldest possible temperature emits radiation, not as a special property of certain materials, but as a fundamental consequence of having atoms in motion. Warm atoms vibrate. Vibrating atoms carry electric charge. Moving electric charges radiate electromagnetic waves. The hotter the object, the faster the atomic motion, the more radiation emitted, and the shorter the peak wavelength of that radiation. A piece of iron at room temperature radiates in the infrared, invisible to human eyes, which is why you can feel warmth from a radiator without seeing it glow. Heat it to roughly 500 degrees on the absolute scale, and it begins to emit the longest visible red wavelengths. At 1000 degrees, it glows clearly red. At 3000 degrees, it glows orange-white. At 6000 degrees, it matches the surface of the sun. The temperature and the spectrum are not independent properties. They are locked together by the same physics. The relationship between temperature and total radiated power is not linear. Gustav Kirchhoff established in 1859 that any material in thermal equilibrium radiates energy at a rate that depends only on its temperature and its surface area, independent of what it is made of. The specific rate was worked out by Joseph Stephan from experimental data in 1879 and later derived theoretically by Ludwig Boltzmann. A surface at twice the temperature radiates not twice as much energy, but 16 times as much. 4 times the temperature means 256 times the radiated power. The temperature dependence is with the fourth power, which means even small increases in temperature produce enormous increases in radiated output. This steep dependence is what allows thermal equilibrium to be reached quickly when the incoming energy is high. A material does not need to rise to extreme temperatures before its radiated output begins to match the incoming rate. It just needs to keep rising until it does. Kirchhoff's 1859 insight connected absorption to emission in a way that closed off any hope for the dust solution. The efficiency with which a surface absorbs radiation is identical to the efficiency with which it emits radiation at the same wavelength. A surface that absorbs half the light at a given wavelength also emits half as much radiation as a perfect emitter at that wavelength. A perfect absorber, one that captures all incoming radiation without reflecting any, is also a perfect emitter, one that radiates the maximum possible output for its temperature. Kirchhoff called this perfect absorber and emitter a Schwarzer-Körper, which translates as black body. The word black here means optically perfect at absorption, not dark in the everyday sense, since a black body at stellar temperatures glows intensely in the visible spectrum. The implications for the dust argument are direct. For the dust to block starlight effectively, it must absorb efficiently across the relevant wavelengths. High absorption efficiency means high emission efficiency. A dust medium that is good at absorbing stellar radiation is equally good at emitting thermal radiation once it heats up. There is no material property that allows high absorption without corresponding high emission. The absorber that works best as a curtain is also the one that glows most intensely when heated. Olbers needed a curtain that absorbed freely and emitted reluctantly. Physics does not offer that combination. The temperature the dust would reach in an Olbers universe has a specific answer. The incoming radiation in that universe is equivalent in intensity to radiation from a stellar surface at several thousand degrees. The dust absorbs that radiation and rises in temperature until the rate of emission matches the rate of absorption. The fourth power relationship means it does not have to rise to stellar temperature immediately. It has to rise to whatever temperature makes the emitted power equal to the absorbed power. For a dust grain soaking up light from a sky as bright as a star's surface in every direction, the equilibrium temperature is the same as the stellar surface providing that light, several thousand degrees. At several thousand degrees, the dust emits light strongly across the visible spectrum. The curtain is glowing at the same intensity as the stars it was supposed to hide. Conservation of energy is the reason this cannot be otherwise. Energy cannot be created or destroyed. A dust grain that absorbs a photon gains exactly as much energy as the photon carried. That energy goes into the thermal motion of the grain's atoms. The grain can distribute that energy internally, transfer it to neighboring grains by collisions, or radiate it away as photons. In a cold, sparse environment, the grain eventually radiates the energy away at a low temperature and then cools. In an Olbers universe, where photons arrive continuously from every direction at stellar intensity, the grain never gets to cool because the incoming rate always restores the lost energy and then some until equilibrium is reached. At equilibrium, the outgoing radiation exactly matches the incoming radiation. The energy is not stored, not lost, not destroyed. It is returned to the radiation field at the same rate it arrived. The net effect on the sky's brightness is zero. The argument does not target dust specifically. It applies to any material placed in the path of the incoming radiation. Gas, rock, liquid, any combination of atoms would behave the same way. The mass of the absorber and its chemical composition determine only the timescale over which it approaches equilibrium. They do not change the equilibrium temperature it reaches or the brightness it emits when it gets there. Any medium proposed to intercept stellar light in an Olbers universe will, if given enough time, come to glow as brightly as the sources it was meant to block. The class of solutions involving interception between source and observer is closed, not for lack of suitable materials, because thermodynamics applies to all materials. What this narrows the problem to is the following. The only way to have a dark sky is to reduce the total amount of energy entering the calculation before it is emitted. Not intercept it after emission, not absorb and re-radiate it. Prevent it from being generated in the first place. Two mechanisms can do this: fewer stars than the infinite distribution requires, so that sightlines in some directions find nothing, or stars that have not been burning long enough to fill the sky, so that the arriving light represents not the sum of infinite emission over infinite time, but the sum of finite emission over a finite lifetime. The first mechanism is what Kepler proposed, and what Newton's gravity made difficult to sustain. The second points toward the resolution, and following it requires knowing what kind of universe allows stars to have a starting point. A universe that started, which is not the eternal universe that classical physics assumed. If the problem is time rather than space, the question becomes how to detect the age of a universe in the data it sends you, and whether any part of that data survives long enough to be read. Standing outside at solar noon on a clear day, you receive roughly 1,000 watts of energy for every square meter of skin facing the sun. That number, the solar irradiance, is one of the most precisely measured constants in physics. 1,000 watts per square meter is enough to warm skin noticeably within seconds, drive a sunburn within minutes, and provide the energy that powers every plant and every weather system on the surface of this planet. One star, from one direction, delivering 1,000 watts per square meter, produces the entire thermal and biological context in which life on Earth exists. The rest of the sky contributes almost nothing by comparison. Point a sensitive instrument at any region of sky away from the sun, and the energy density is so much lower that it barely registers against the solar input. This asymmetry, one star blazing from one direction and nearly nothing arriving from everywhere else, is the specific energy environment that Earth's biochemistry is built for. In the universe, Olbers' paradox describes, every patch of sky delivers energy at the rate the sun's face delivers it. Not the rate the sun delivers it to Earth at this distance, but the rate at which the sun's surface itself emits. The difference is significant. The sun appears as a disk covering less than 1/100% of the visible sky. What arrives at Earth is the sun's total output spread thin across a large sphere centered on the sun. Scale that delivery up so that every part of the celestial sphere is as bright as the sun's disk, and the numbers grow by a factor of roughly 20,000. 20,000 times the energy of solar noon, arriving from every direction simultaneously, means somewhere in the range of 20 million watts per square meter, pressing on any surface from all sides at once. The comparison that comes closest in human experience is not summer heat or even a furnace. It is the interior of a nuclear detonation, where temperatures reach the same order of magnitude and matter loses its organization into solid objects within microseconds. The relevant damage begins far below those extremes. Long before rock vaporizes and iron boils, the chemistry of living systems fails at temperatures orders of magnitude lower. Proteins, which are the molecular machines that carry out every function inside a cell, fold into their working shapes through a combination of chemical bonds and thermal motion calibrated to a narrow temperature range. Above roughly 45 degrees Celsius, most proteins begin to unfold. The shapes that allow them to catalyze reactions, bind to other molecules, and carry signals across membranes dissolve into disordered chains. A cell whose proteins have denatured is not a cell under stress. It is a cell that has lost the structural basis for being a cell. DNA survives somewhat higher temperatures than proteins before its double helix begins to separate, but the range is not wide. And the radiation content of an Olbers universe includes not just the visible wavelengths that warm surfaces, but the full thermal emission spectrum of a 6,000-degree source, which extends strongly into the ultraviolet. Ultraviolet light damages DNA directly by causing chemical changes to specific base pairs, the rungs of the genetic ladder. Organisms on Earth today have repair mechanisms for ultraviolet damage because the sun delivers some UV even through the atmosphere. In an Olbers universe, those repair mechanisms would be irrelevant. The incoming UV flux would fragment DNA faster than any repair process could operate. The question of whether a living organism could persist in that environment is not a question of resilience. It is a question of whether the concept of molecular repair can function when the rate of damage exceeds the rate of synthesis by many orders of magnitude. The radiation field in that universe does not merely heat surfaces and break chemical bonds. Light carries momentum, and light that is absorbed or reflected transfers that momentum to the absorbing or reflecting surface. This is radiation pressure. Ordinary sunlight exerts a radiation pressure on every surface it strikes, but the force is so small that it only matters in specialized contexts, such as the slow spiral of a comet's tail away from the sun or the trajectory corrections needed for long-duration spacecraft. In a radiation field 20,000 times more intense than solar noon, from every direction simultaneously, the radiation pressure becomes a significant physical force acting on matter from all sides. The equilibrium this creates is not merely a thermal equilibrium. It is a mechanical one, where matter is being continuously compressed and buffeted by the momentum of the light field rather than simply heated by its energy. None of this reaches the level of physical consequence for a simple reason. The sky is dark. The reason is not that we have some shielding from this radiation. We are not protected from it by any intervening material. The radiation simply is not there. The energy is not being produced, because the stars that would produce it have not been burning for infinite time. The dark sky is not a neutral backdrop. It is the evidence that the universe has a finite budget of stellar energy that has reached us, and that budget is small enough to permit chemistry, biology, and the existence of observers standing in the night asking why it is dark. This is the reframe the paradox demands if you follow the thermodynamics further than the optics. The question is not merely about what you see when you look up. It is about the total energy density of the radiation field in which matter is immersed. The universe you are sitting inside right now has a radiation energy density that is specific, measurable, and consistent with the existence of complex organized matter. That density is not zero, because the cosmic microwave background fills space uniformly, but it is equivalent to a temperature of roughly 2.5 degrees above absolute zero, not thousands of degrees. The difference between 2.5 degrees and 6,000 degrees is the difference between a universe that allows atoms to form molecules and a universe in which every chemical bond is continuously destroyed. Every process inside a living cell operates within a window defined by the thermal environment the dark sky creates. Enzymes work at body temperature because they evolved in a world where body temperature was physically achievable and sustainable. The genetic code uses 4 nucleotide bases because those bases are chemically stable at the temperatures liquid water allows. The speed at which proteins fold, signals propagate, and membranes maintain their selective permeability, all of these rates are tuned to the narrow thermal range between the freezing and boiling points of water at normal pressure. Water is liquid in that range because the dark sky permits it. A sky at stellar surface temperature means no liquid water anywhere on any planet's surface at any distance from any star. The thermal environment that permits water to be liquid, and therefore permits biochemistry as we practice it, is not an independent fact about chemistry. It is a downstream consequence of the sky being dark. The total energy produced by stars in an infinite, eternal universe, sent outward in all directions without limit and without end, would fill space to stellar surface temperature and leave no room for organized matter anywhere. The paradox, stated as an energy problem rather than a visibility problem, asks why this has not happened. The answer cannot be absorption, as the thermodynamics shows. It cannot be a finite star count, as gravity shows. It has to be something that limits the total energy output of the stellar population before the radiation field reaches equilibrium. The only mechanism that accomplishes this is time. Stars that have been burning for a finite period have produced a finite amount of energy. That energy, spreading outward at the speed of light, has filled only the volume of space light can cross in the time available. Beyond that volume, no stellar energy has yet arrived. The radiation field is not in equilibrium with stellar surfaces. It is younger than the stars, carrying only as much energy as has been emitted since the stars first ignited. The dark sky is not missing light that is being absorbed somewhere along the way. It is missing light that has not yet been made. The universe is too young. How young, and what that youth looks like written in the sky, is the question the next piece of this has to answer. In February of 1848, almost exactly a year before his death, Edgar Allan Poe delivered a lecture in New York City on the nature of the universe. He had prepared a written version, a long prose work he called Eureka, and he considered it the most important thing he had ever written. He sent a copy to the scientist and explorer Alexander von Humboldt, one of the most respected naturalists of the age, with a note asking for his reaction. Humboldt, so far as the record shows, did not reply. The scientific establishment of the time had no particular reason to read a prose poem written by the author of The Telltale Heart as a contribution to cosmology. The question of why the night sky was dark had occupied serious mathematical minds for more than 2 centuries. Poe's argument in Eureka covered a great deal of ground, some of it wrong and some of it speculative, in ways that the physics of the time could not evaluate. But buried inside it, stated with surprising clarity, was the correct resolution to the dark sky paradox. He described the problem explicitly. If stars extended through space in every direction without limit, then every line of sight from the observer's eye should terminate on the surface of one. The sky should blaze uniformly. It does not. His explanation for why it does not was simple and did not require any new physical mechanism. The universe, he argued, is not old enough. The most distant stars have been sending their light toward us since they formed, but that light has not finished the journey. The voids in the star field that telescopes reveal everywhere they look are not regions where stars are absent. They are regions where the stars exist, but their light has not yet had time to arrive. The argument can be restated in terms of a letter. Someone sits down far away and writes a letter and sends it. The letter is real. It is on its way, but it has not arrived yet. If you check the mailbox, you find nothing, and you might be tempted to conclude that no letter was sent. You would be wrong. The absence from the mailbox is not evidence of absence from the world. The dark sky, on Poe's reading, is the mailbox. The letters are in transit. Every direction that looks empty is a direction where light from a distant star is traveling toward us and has not yet reached us, because the star has not been burning long enough and the distance is too great for the time available. The darkness is not a void. It is an unreceived message. What makes this insight striking is not its complexity. It is its simplicity. The astronomers who had wrestled with the paradox for 2 centuries had looked for physical mechanisms, something to absorb the light, some edge to the star distribution, some gravitational argument for the configuration of matter. Each mechanism introduced new problems. Poe bypassed all of them by asking a different question. Not what happens to the light after it is emitted, but whether it has had time to arrive. The answer required no new physics. It required only accepting that the universe had a finite age. Accepting a finite age was not a small step. It meant accepting that the universe had a beginning. In 1848, the dominant cosmological assumption was that the universe had existed forever. An eternal universe had no beginning to explain and required no cause. A universe with an age raised immediate questions about what came before the age began, and those questions sat in territory where physics had no tools and philosophy had no consensus. Poe did not solve those questions. He stepped over them by treating the finite age as a logical necessity rather than a philosophical problem. If the sky is dark and the geometry demands it should be bright, then the only escape is that the universe has not been running long enough for the geometry to be realized. Poe also stated something that went further than the dark sky argument. He described the universe as having originated from a condition of extreme simplicity and unity, and as having expanded outward from that origin. He described the distribution of matter through space as the result of a process of outward motion from a single point. The idea that the universe began in a state of extreme compression and has been expanding ever since, which became the cornerstone of 20th century cosmology, appeared in a literary work in 1848. Poe had no way to quantify this. He had no evidence for it in the contemporary data. He was reasoning from aesthetic and philosophical principles about simplicity and unity. But the structure of his cosmology, a universe with a beginning, expanding from a point of origin, was closer to the picture that observations would eventually support than anything the professional astronomers of his time were prepared to consider. Poe was not right about everything in Eureka. Some of his reasoning was wrong, and some of his claims about the physical nature of matter and force had no basis in the science of his time. He treated gravity and electricity as manifestations of the same underlying force, which was speculative in a direction that later physics did not confirm. He described stars and planets as having formed from the condensation of an original material by gravity, which was roughly correct, but his mechanism was closer to intuition than to derivation. The work read, in places, more like a philosophical essay than a physical argument. What survived scrutiny was the specific logical move about time. That the sky is dark because the universe is young was the one claim in Eureka that turned out to be correct, and that the scientific tradition had not yet produced on its own terms. The reception of Eureka tells a specific story about how knowledge moves, or fails to move, between disciplines. The work was reviewed in literary circles, not scientific ones. Astronomers who encountered it found it easy to dismiss. It had no mathematics. Its arguments were not structured in the form that physical science required. The author was known for fiction and verse, not for optics or celestial mechanics. The correct answer to a problem that had occupied scientific thought since Thomas Digges in 1576 sat in a published document for another 80 years before it was reached independently by scientists working within the problem formale tradition. The independent rediscovery came through several people working in the late 19th and early 20th centuries who began treating the dark sky as a problem about the age and extent of the universe rather than the transparency of the sign. Medium between stars. William Thomson, who is better known as Lord Kelvin, addressed the problem in a lecture in 1901 and provided a quantitative version of the time argument. He calculated how old the universe would need to be for starlight from all distances to have filled the sky, and found that the number was far larger than the age suggested by other physical arguments. The sky was dark because stars had not been burning long enough to fill it. This was Poe's argument, stated in the language of numbers. The gap between Poe's statement in 1848 and Lord Kelvin's lecture in 1901 is 53 years. During those 53 years, the correct resolution to the paradox was available in print, in a book that remained in circulation. The question of who counts as having first understood something is not always easy to answer when the understanding crosses the boundary between literary and scientific expression. What Poe demonstrated was that the core logical step did not require mathematics to see. It required only asking whether a universe of finite age could have filled the sky. The mathematics, when it came, confirmed what the logic had already suggested. The age of the universe was not a quantity anyone could measure in 1848. It was not a quantity anyone could measure for another century. What it took to go from Poe's intuition to a number on a page was a set of observations that nobody had yet made, of a kind of light that nobody had yet thought to look for, from an era of the universe that nobody yet knew had left a trace. What that trace looks like, and what it took to find it, is where the long detour through wrong answers finally connects to a universe with an address in time. Count the seconds between a lightning flash and the thunder that follows it. Every 3 seconds of delay means the strike was about 1 kilometer away. The sound took that long to travel from the point of discharge to your ear. The flash arrived almost instantly, because light crosses a kilometer in a tiny fraction of a millisecond, far faster than any human sense can detect the delay. The sound was slow enough to feel. What that gap between flash and thunder tells you is something precise. It tells you that the event you witnessed did not happen where you are standing, and it did not happen at the moment you heard it. It happened at a distance, and information about it traveled to you at a finite speed. By the time it reached you, it was already in the past. This is not a quirk of thunderstorms. It is the structure of all observation. Every piece of information about the world arrives at your senses after traveling from its source, and the travel takes time, however short. When you look at an object across the room, the light bouncing from it takes a few nanoseconds to cross the distance. The image you see is of the object as it was a few nanoseconds ago. For objects at the scale of a room, this lag is too small to matter. For objects at astronomical distances, it changes everything about what seeing means. Light travels at roughly 300,000 kilometers per second. That is fast enough to circle the Earth 7.5 times in a single second. Fast enough to cross the distance between New York and Los Angeles in about 16 thousandths of a second. Fast enough that for most purposes in ordinary life, the travel time is indistinguishable from zero. But space is not ordinary. The distances between objects in space are measured in units of how far light travels in a year, a month, a minute. And those units, when you look at what they correspond to in kilometers, quickly reach numbers where the travel time of light becomes not a correction to be applied, but the dominant fact of the observation. The moon sits roughly 380,000 kilometers from Earth. Light covers that distance in about 1.25 seconds. When you look at the full moon rising, the image your eye receives is the moon as it was 1.25 seconds ago. This is not a philosophical quibble, it is a physical fact. If something changed on the lunar surface at the moment you were looking, you would not see it yet. You would see it in just over a second. The sun is farther. Light takes roughly 8 minutes and 20 seconds to cross the 93 million miles between the solar surface and Earth. The sun you see at any moment is the sun as it was 8 minutes ago. If the sun were somehow extinguished at this instant, the sky would not go dark for 8 minutes. The last light has already left. It is on its way. Scale further outward and the delays become years, then centuries, then millions of years. The nearest star beyond the sun is Proxima Centauri, sitting about 4.25 light years away. The light arriving from it tonight left its surface 4.25 years ago. Proxima Centauri, as it exists right now, is invisible from Earth, because no information about its present state has yet had time to reach us. The star you see is the star as it was in the recent past. The center of our galaxy, where hundreds of billions of stars crowd together around a massive central object, is about 26,000 light-years away. The light from those stars that reaches us tonight shows us the galactic center as it was 26,000 years ago, at a time when anatomically modern humans were painting on cave walls in France and the Sahara was green with vegetation. The galaxy, as it looks now, will not reach us for another 26,000 years. The Andromeda Galaxy, the nearest large galaxy to our own and just visible to the naked eye as a faint smudge on a clear, dark night, is about 2.5 million light-years away. Looking at it is looking 2.5 million years into the past. The galaxies visible through a telescope, running to distances of hundreds of millions and billions of light-years, appear as they were hundreds of millions and billions of years ago. The most distant objects astronomers have imaged so far are seen as they appeared when the universe was less than 1 billion years old, in some cases only a few 100 million years after the first stars formed. These are not reconstructions or inferences. They are direct observations of light that left its source billions of years before the Earth existed. The night sky is therefore not a picture of where things are. It is a picture of when things were. Every source you see represents a different era, a different moment in the universe's history, all arriving at your eye simultaneously and overlapping into one composite image. A star 500 light-years away appears as it was 500 years ago. A galaxy 2 billion light-years away appears as it was 2 billion years ago. The photons arriving at your retina on any given night were emitted across an enormous range of times. The sky is a mosaic of different pasts, assembled into one present moment on the surface of your eye. There is a specific consequence of this mosaic structure that is easy to overlook. When astronomers map the distribution of galaxies, they are not mapping where galaxies are. They are mapping where galaxies were at the time their light left them. A galaxy seen at a distance of 500 million light-years appears as it was 500 million years ago. A galaxy seen at a distance of 5 billion light-years appears as it was 5 billion years ago. A map that combines observations at different distances is combining observations from different eras. The universe does not have a single current state that can be photographed. Every image of it is already a composite of different moments. The deeper you look into space, the further back in time you reach, until the observable boundary is not a wall in space but the beginning of the era in which light could travel freely at all. This is the mechanism that connects the finite speed of light to the finite age of the universe in a way that resolves the dark sky paradox. The observable universe is not limited by the spatial extent of matter. It is limited by how far light could have traveled in the time available. The universe has been running for roughly 13,800 million years. Light traveling since the moment of origin has covered a distance of roughly 13,800 million light-years in that time. Objects whose light has not yet had time to reach us, objects that are real and exist and are presumably full of stars, are simply outside that limit. Their light is in transit. it has not arrived. The directions of sky where they sit look dark not because those directions contain nothing, but because the messages from those directions have not yet completed the journey. The size of the observable universe, the volume of space from which we have received any light at all, is therefore a statement about the age of the universe and the speed of light combined. More time means more observable volume. A younger universe means a smaller observable volume. And a smaller observable volume means fewer shells of stars that have had time to contribute their light. The darkness in most of the sky is not missing stars. It is the frontier of undelivered messages, the region where light from real sources is traveling toward us and has not yet finished. What sits at the outer edge of the observable universe is not empty space. It is the earliest light that has had time to arrive, the first photons, from the earliest era that was capable of producing them, reaching us now after the longest possible journey. That light is not starlight. It is older than any star, and it is visible, but not to the eye. What that oldest light is, where it came from, and why it fills the entire sky from every direction equally, is the place where the paradox stops being about absence and starts being about what is there. The answer to the dark sky paradox is now available in full, not absorption, because thermodynamics shows any absorber reaches the temperature of the sources behind it, not a finite distribution of stars, because Newton's gravity shows a bounded cluster collapses, not an eternal universe of stars in infinite space, because an eternal universe would have had infinite time to fill every point of space with radiation at stellar temperature. The sky is dark because the universe has a finite age, and stars have not been burning long enough for light from most of them to have reached us. This answer has the structure of what Lord Kelvin and Edgar Allan Poe each identified, from different directions, as the only remaining option after the others were closed. It is also the answer that Edward Robert Harrison placed on firm quantitative ground in his 1987 book, Darkness at Night, where he worked through the precise contributions of each proposed cause and showed which one carried the weight. The specific calculation runs as follows. The universe is approximately 13,800,000,000 years old. Light travels at a fixed speed. The maximum distance from which any light could have reached us is therefore the distance light can cover in 13,800,000,000 years, which is roughly 13,800,000,000 light years. Stars at greater distances exist. Their light is traveling toward us, but it has not arrived, and it will not arrive for billions of years yet. The shell argument, which showed that every distance band contributes equally to the sky's brightness, and that infinite shells add up to infinite brightness, assumed that every shell had had time to deliver its contribution. In a universe of finite age, most shells have not. The shells within the observable horizon contribute their equal amounts. The shells beyond the horizon contribute nothing, not because they lack stars, but because they lack time. Harrison's contribution was to separate this finite age effect from a second effect that had often been conflated with it in earlier discussions. The universe is expanding. Galaxies are not sitting still in space while light crosses the distance between them. They are receding, and the space itself is stretching. A photon traveling from a distant galaxy toward Earth is traveling through space that is continuously expanding beneath it. The wavelength of the photon stretches with the space. By the time the photon arrives, its wavelength is longer than when it was emitted. A longer wavelength means lower frequency. Lower frequency means lower energy. A photon that left its source as visible blue light may arrive as infrared, invisible to human eyes. A photon from a sufficiently distant source may arrive as a microwave, stretched by a factor of 1,000 or more. Both effects make the sky darker, but they are different in kind, and Harrison showed they are different in magnitude. The finite age effect is primary. It eliminates most of the shells from contributing at all. The expansion effect reduces the energy of the photons from the shells that do contribute. If the universe had the same age but no expansion, the sky would still be overwhelmingly dark because almost all of the shells would still be outside the observable horizon. If the universe had expansion but infinite age, enough time would have passed for light from every shell to have arrived, though it would be redshifted, and the sky would still be bright. The darkness comes mainly from the fact that the universe is young enough that most sightlines, extended to infinite distance, encounter their first star in a region whose light has not yet arrived. The redshift adds additional dimming on top of this, but it is the finite age that closes off the paradox. The edge of what we can see is therefore not a wall. It is a horizon, and a horizon of a specific kind. Stand on flat ground and look toward the horizon in every direction. The horizon is not where the land ends. It is where the curvature of the earth means the ground is no longer in your line of sight. Walk toward the horizon, and new ground comes into view ahead, while ground vanishes behind. The cosmic horizon works by the same geometry in time. As the universe ages, new light that has had time to travel from previously unreachable regions arrives for the first time. The observable universe expands, not because space is growing, but because time is passing and light is covering more ground. A region that was outside the observable universe yesterday is, in principle, inside it today, by whatever tiny increment light travels in one day. The total number of stars that have contributed any light to our sky is finite, with the observable universe containing hundreds of billions of galaxies, each with hundreds of billions of stars, but it is not the infinite count that makes Olbers' paradox inescapable. The shells within the horizon, even accounting for their equal brightness contribution by shell, do not sum to a sky as bright as a stellar surface. Edward Robert Harrison's calculation showed that the total accumulated stellar light in the observable universe, if spread uniformly across the entire sky, would produce a sky roughly 10 trillion times dimmer than Olbers' result. The dimming factor from finite age is not a small correction. It is the entire gap between the bright sky, the paradox demands, and the dark sky we observe. The ratio between the brightness the paradox demands and the brightness we observe is a useful number to hold. The Olbers' bright sky would deliver energy equivalent to standing on the surface of an average star. The actual night sky, excluding the sun, delivers energy roughly 10 trillion times less than that. The entire gap is accounted for by the limited number of stellar shells within the observable horizon and the reduced energy of their photons due to cosmic expansion. There is no missing piece. The accounting closes. One number sits inside this that deserves a moment. The light reaching us from the most distant observable galaxies has been traveling for roughly 13 billion years. Those galaxies emitted that light when the universe was only a few 100 million years old. In the time since then, the universe has expanded by a factor of roughly 10 in linear scale. A photon emitted in visible light from those galaxies has had its wavelength stretched by the same factor. It arrives not as visible light, but as near infrared, beyond the range the human eye responds to. The most ancient stellar light in the observable universe is, in this sense, already invisible to unaided eyes. The expansion has shifted it out of the visible range, adding its dimming on top of the dimming from finite age. But stars are not the oldest source of light in the universe. Before the first star ignited, before any nuclear fusion had begun anywhere in space, there was an earlier era when the universe itself was the source of radiation, not because of stars, but because the early universe was hot enough and dense enough that matter and light were in thermal equilibrium across all of space simultaneously. The light from that era predates all stars. It left its source not from individual point sources scattered through space, but from the entire volume of the early universe at once. When that era ended and the universe cooled enough to become transparent, that radiation streamed outward in all directions and has been traveling ever since. It should still be arriving. It should fill the sky from every direction equally, and it does. But expansion has stretched it in the intervening time by a factor of roughly 1,000. What was thermal radiation at a temperature of about 3000 degrees on the absolute scale? Bright orange-red light has been stretched into microwaves, radiation with wavelengths of a few millimeters, corresponding to a temperature of about 2¾ degrees above absolute zero. This is not visible. It is not detectable with eyes or with ordinary optical instruments. But it is there, filling the sky from every direction, uniform to a precision of about 1 part in 100,000. It is the oldest light in the observable universe, and it was not discovered by looking through a telescope. How it was found, and what it says about the universe that produced it, connects the dark sky paradox to a measurement that no one was looking for when it appeared. The darkness between the stars is not just a condition that has been explained, it is a measurement. The specific brightness level of the night sky encodes a quantity about the universe, in the same way that the temperature of a cooling object encodes how long it has been cooling. Look at the night sky carefully enough, and you are reading an instrument, one that has been running since the first stars ignited, and whose current reading corresponds to a specific elapsed time. The reading is dim. And that specific level of dimness, matched against what an infinite, eternal universe should produce, gives a number for how old the universe is that turns out to agree with every other method developed to measure the same thing. For most of the history of the dark sky paradox, the age of the universe was not a measurable quantity. It was a metaphysical category. The universe had either always existed, in which case its age was infinite, or it had been created at some point, in which case the moment of creation was outside the reach of physics. Neither position produced a number. What converted the age of the universe from a philosophical position into a physical measurement was the discovery that the universe is expanding. Georges Lemaitre, a Belgian physicist and Catholic priest, worked out the mathematics of an expanding universe in 1927. He was working with the equations of general relativity, which Albert Einstein had published a decade earlier, and he noticed that they had solutions in which the distances between galaxies grew over time. If galaxies were receding from each other now, they had been closer in the past. Run the equations backward far enough, and everything converges. There was a moment when all the matter in the universe occupied a vastly smaller volume. Lemaitre called this the primeval atom, a single compact origin from which the current universe expanded. Einstein initially resisted this. He had added a term to his own equations specifically to prevent them from predicting a dynamic, changing universe. An eternal static universe was the assumption he brought to the mathematics, and he adjusted the math to preserve it. He later described this adjustment as the greatest mistake of his career. Edwin Hubble provided the observational confirmation in 1929. Measuring the spectra of light from distant galaxies, he found that the wavelengths were systematically shifted toward the red end of the spectrum, with the amount of shift proportional to the galaxy's distance. This redshift meant the galaxies were receding, and the farther away a galaxy was, the faster it was moving. The pattern was consistent with an expanding space that was carrying all the galaxies apart from each other simultaneously, with no center and no edge, but with every pair of points in the universe increasing their separation over time. This was Lemaitre's expanding universe, observed directly. The universe was not static, it was moving, and measuring the current rate of its movement could tell you how long ago it had been in one place. The rate of expansion is quantified by a number called the Hubble constant, which describes how fast the distance between galaxies is growing per unit of distance. If you know the current expansion rate and the physics of how that rate has changed over time, you can calculate when all the matter was at the same point. The first estimates of the Hubble constant, worked out by Hubble himself from his 1929 data, gave an age of roughly 2 billion years. This created an immediate problem. The known ages of certain stars and rock formations on Earth already exceeded 2 billion years. A universe younger than objects inside it is a contradiction that the measurement could not survive. It survived because the initial measurements of the Hubble constant were wrong. Hubble had miscalibrated the distance scale, and the error compounded. decades of progressively refined measurements gradually pushed the age estimate upward. By the end of the 20th century, independent methods, including the expansion rate, the ages of the oldest stars, and measurements of the cosmic microwave background, had converged on an age of roughly 13,800,000,000 years. What the darkness of the night sky does with this number is confirm it from a completely different direction. The total brightness of the extragalactic background light, the diffuse glow produced by the sum of all galaxies at all distances that have had time to send light here, is measurable with sufficiently sensitive instruments placed outside the solar system's own scattered light. The measured value is consistent with roughly 13 billion years of stellar light production distributed through the observable volume. If the universe were twice as old, the background would be approximately twice as bright. If it were half as old, it would be half as bright. The darkness, read as a number, gives an age that matches the expansion measurements. Two completely different instruments, one measuring the recession of galaxies and one measuring the accumulated glow of their stars, give the same answer. The image that comes to mind is a clock whose face is made of the sky itself. The hands of that clock are the brightness of the night between the stars, and they advance as the universe ages and accumulates more stellar light. At the current position of the hands, the universe is approximately 13,800,000,000 years old. An observer in the far future would see a brighter sky, not because any new mechanism has appeared, but because more shells of stars will have had time to deliver their light. An observer in the distant past would have seen a darker sky, with the observable volume smaller and fewer stars having had time to contribute. The darkness you see when you look up is a reading on this clock, taken tonight, from this particular moment in cosmic history. There is a subtlety the expansion measurement adds to this picture. The shells of stars contributing to the night sky brightness are not contributing equally to the final tally, because the photons from more distant shells have been traveling through expanding space. As space expands, the wavelength of each photon stretches with it. A photon emitted by a galaxy 10 billion light-years away has been traveling for 10 billion years through a universe that has been expanding the whole time. Its wavelength on arrival is longer than its wavelength at emission. Longer wavelength means lower energy. A photon stretched from visible blue light to infrared carries less energy than when it started. The shell still contributes to the night sky brightness count, but it contributes less than the same shell would in a non-expanding universe. The expansion is not the dominant cause of the darkness, as the finite age argument is, but it is a real secondary contribution that reduces the energy of every photon from every distant source. The oldest photons in the observable universe have been stretched the most. Light from the edge of the observable horizon has been traveling for roughly 13,800,000,000 years through a universe that has expanded by a factor of more than 1,000 since that light was emitted. Its original wavelength, whatever it was, has been stretched by that same factor. Light originally emitted in the optical or near-infrared has been shifted into the microwave range, arriving with wavelengths measured in millimeters rather than hundreds of nanometers. The energy per photon has been reduced by the same factor of 1,000. The contribution to the visible sky brightness from these oldest sources is negligible, not just because of their distance, but because their light has been drained of nearly all its visible wavelength energy by the expansion. The question that follows from this is about the photons that have been stretched the most of all, from a source older than any star. Light from the era before stars existed, emitted when the universe was uniformly hot and dense, would have been stretched by a factor even larger than the light from the most distant galaxies. That light, if it survived the journey, should be arriving now, already completely invisible to ordinary detection, in a range of wavelengths that tells you the temperature of the universe at the moment it was emitted. What wavelength range it should occupy, what temperature it corresponds to, and what it would look like to an instrument that could see it, is the next layer of the story the sky has to tell. Stand near a road and listen as an ambulance passes. Before it reaches you, the siren is high-pitched, urgent. After it passes and moves away, the pitch drops, lower and more muted, even though the siren itself is producing exactly the same sound at the same volume. The change in pitch is not a property of the siren. It is a property of your position relative to the siren's motion. The waves of sound the ambulance emits are being compressed as it approaches you, arriving at your ear more frequently than they would from a stationary source. As it moves away, the opposite occurs. Each successive wave is emitted from a position slightly farther than the previous one, so the waves are stretched, arriving less frequently. Lower frequency means lower pitch. This is the Doppler effect, and it applies to any wave whose source and observer are moving relative to each other. Light behaves the same way for sources moving through space. A galaxy moving away from us emits light whose waves are stretched on their way here, arriving with a longer wavelength than at emission. Longer wavelength in visible light means a shift toward the red end of the spectrum, which is why the phenomenon is called redshift. A galaxy moving toward us would have its light blue shifted, compressed to shorter wavelengths. Edwin Hubble's 1929 measurements showed that distant galaxies were systematically redshifted, and the amount of redshift increased with distance. He interpreted this initially as the Doppler effect, as galaxies moving away from us through space at velocities proportional to their distance. The interpretation was not wrong as a description of what was observed, but it missed something important about the physical cause. For nearby galaxies, the Doppler picture is adequate. The recession velocities are well below the speed of light. The Doppler formula gives accurate results, and the galaxies can reasonably be thought of as moving through space in a conventional sense. For galaxies at distances of billions of light years, the picture changes. The recession velocities implied by their redshifts can exceed the speed of light, which is not a violation of relativity, but is also not possible if galaxies are moving through space in the ordinary sense. What is happening is not that distant galaxies are moving through space at enormous velocities. It is that the space between us and them is expanding. The galaxies are, in a meaningful sense, approximately stationary in their local regions of space, but the space itself is growing, and as it grows, the distances between all pairs of points in it increase simultaneously. The light crossing that expanding space is affected not by the motion of its source, but by the growth of the medium it is traveling through. The mechanism is precise. A photon is emitted by a galaxy at a specific wavelength. It begins traveling through space toward us. As it travels, the universe expands. The section of space the photon just crossed is now slightly larger than when the photon crossed it. The wavelength of the photon stretches in proportion to the expansion of the space it occupies. By the time the photon arrives at our eye or our instrument, it has been stretched by the total factor by which the universe has expanded since the moment of emission. If the universe has expanded by a factor of 2 since a photon was emitted, the photon's wavelength is twice what it was at emission. A factor of 10 expansion means a wavelength 10 times longer. A factor of 1,000 means a wavelength 1,000 times longer. Astronomers measure this stretching with a number called the redshift, usually denoted Z. A galaxy with a redshift of 0 is essentially not receding relative to us. A galaxy with a redshift of 1 has its light shifted so that the wavelength upon arrival is twice the wavelength at emission, meaning the universe has doubled in linear scale since the light left. A redshift of 7, corresponding to some of the most distant galaxies detected with modern instruments, means the universe was roughly 1/8 its current linear size when the light was emitted. The cosmic microwave background, the oldest light that can reach us, has a redshift of approximately 1,100. The universe was 1,100 times smaller in linear scale when that radiation was released. Every photon in the cosmic microwave background has had its wavelength stretched by that factor, and its energy reduced by the same factor, since it left its source. Energy and wavelength are not independent properties of a photon. The energy of a photon is inversely proportional to its wavelength. Double the wavelength, and you have the energy. A photon that began its journey as visible blue light with a wavelength of around 400 nanometers arrives after a redshift of 1000 with a wavelength of around 400 micrometers. That is in the microwave range. Its energy has been reduced by the same factor of 1000. The photon is the same photon, traveling continuously since it was emitted. No energy has been destroyed. The energy has been transferred to the gravitational field of the expanding universe, spread out across the expansion itself. The universe gets slightly colder as it expands, and each photon in it carries slightly less energy, because the energy has gone into the work of expanding space. For the dark sky paradox, the redshift adds a specific dimming layer beyond what geometry alone predicts. In a static universe, the brightness of a source falls as the inverse square of its distance. In an expanding universe, there are two additional factors. Each photon from a redshifted source carries less energy than it started with, by a factor of 1/1 plus the redshift. And those photons arrive less frequently than they would from a source at rest, because the time between photon emissions is also stretched by the same expansion factor. Combined, these two effects reduce the apparent brightness of a source by an additional factor of 1 divided by the square of the quantity 1 plus the redshift, beyond the inverse square reduction from distance. For a galaxy at redshift 1, the additional dimming factor is 1/4. For a galaxy at redshift 7, the additional dimming is 1/64. For the microwave background, with its redshift of 1100, the additional dimming factor is 1 divided by the square of 1100, which is approximately 1 part in 1,200,000. The farthest sources visible to our best instruments, the most ancient galaxies, contribute almost nothing to the visible sky brightness, not just because they are far away, but because their light has been drained of visible wavelength energy by the expansion. Light that left those galaxies as visible or ultraviolet radiation has arrived as infrared, completely outside the range our eyes respond to. The sky looks dark in visible wavelengths partly because the energy of distant starlight has migrated out of the visible range during transit. This is the secondary dimming effect working alongside the primary effect of finite age, reducing the contribution of every distant shell below what a non-expanding universe would receive. The ambulance analogy captures the direction of the shift accurately, but not the mechanism. In the ambulance, the source moves through space, and the waves it emits are longer or shorter depending on the direction of travel. In the expanding universe, neither the source nor the observer is moving through space in any unusual way. The space between them is growing, and the waves stretch with it. The result looks similar in both cases, a shift to lower frequency that grows with the source's recession, but the physics is different, and the difference matters when you ask whether the redshift could in principle be reversed, or whether it represents a permanent change in the photon. The question the redshift raises for the paradox is quantitative. Both the finite age and the expansion-related dimming are making the sky darker than Olbers predicted. But they are doing so by different mechanisms and by different amounts. Knowing which one does more of the work determines what kind of universe would be needed to produce a bright sky, and what kind of observation would distinguish them. Which of the two effects carries more of the weight, and by how much, is something that can be calculated, and the answer changes what you conclude about the structure of the problem. Two effects are working together to keep the sky dark. The universe has a finite age, which cuts off most of the shells of stars before they can contribute. And the universe is expanding, which reduces the energy of the photons from the shells that do contribute. Both are real. Both make the sky dimmer. The question of which one does more of the work has a specific quantitative answer, and the answer matters because it determines what kind of universe would be needed to produce a bright sky. The cleanest way to separate the two effects is with a pair of thought experiments. Picture a universe with the same age as ours, the same density of stars, the same luminosity, but no expansion at all. A static universe in which galaxies sit where they are and light travels without having its wavelength stretched. In that universe, the shells beyond the observable horizon still contribute nothing because the finite age still prevents their light from arriving. The observable horizon is still roughly 13,800,000,000 light-years away. The shell argument still fails to sum to an Olbers bright sky because most of the shells are missing. The sky in that static but same-age universe is essentially as dark as the sky we observe. Removing expansion from the calculation barely changes the result. Now run the second thought experiment. Take the expanding universe, with its stretching of photon wavelengths and its reduction of photon energies, but remove the finite age. The universe has always existed. Stars have been burning forever. Every shell has had infinite time to deliver its contribution. The redshift does reduce the energy of distant photons, and it does so more severely for more distant sources, but it does not eliminate the contribution from any shell entirely. The sum of all the redshifted contributions from all the shells still converges to a sky much brighter than what we observe. An infinitely old expanding universe would have a significantly bright sky, not as catastrophically bright as the static infinite universe Olbers described, but far brighter than the sky overhead tonight. The redshift alone is not enough to produce the darkness we see. The two thought experiments together make the comparison precise. Finite age without expansion gives essentially the dark sky we observe. Expansion without finite age gives a sky too bright to match observation. The darkness is predominantly the product of finite age, and the expansion is a secondary contribution that would not, by itself, solve the problem. Edward Robert Harrison quantified this separation carefully in his analysis of the paradox. He found that the fractional contribution of expansion to the sky's darkness, compared to what the same universe would look like if expansion were somehow switched off while preserving the finite age, is relatively small. The overwhelming share of the work is done by the boundary of the observable universe, the horizon set by the finite time available for light to travel. This creates a small correction to how the paradox is often described in popular accounts. A common version of the resolution states that the sky is dark because the universe is expanding, and that the redshift of distant starlight into infrared wavelengths is what removes the brightness. That version is not wrong, but it is misleading about which effect is primary. A better statement is that the sky is dark because the universe has not been running long enough for light from most stars to arrive, and the expansion provides an additional dimming on top of this. The distinction is not merely pedantic. It points to which property of the universe is doing the essential work, and an expanding universe that had been running forever would not have a dark sky in visible wavelengths. There is a specific way to see why popular accounts get this backward. Expansion is a more visually dramatic concept than age. The idea that the universe is stretching and that light is being stretched with it is memorable and counterintuitive in a satisfying way. The idea that the universe simply has not been running long enough is almost too plain. It does not require any exotic mechanism. It requires only a beginning, and a beginning is harder to picture than a stretching. The result is that many accounts of the dark sky reach for the more dramatic mechanism and assign it the primary role, leaving the impression that if you could somehow freeze the expansion while keeping everything else the same, the sky would brighten to the level Olbers predicted. That is not what would happen. Freeze the expansion but keep the finite age, and the sky remains essentially as dark as it is now. The finite age is the load-bearing element of the resolution. The expansion is a genuine but secondary refinement. Think of two valves that are both partially closed on a water line feeding into a tank. The tank stays nearly empty. Now consider that the first valve is almost completely shut, allowing only a tiny trickle through. The second valve is partially open but restricts flow by roughly half. If you open the second valve fully, the tank fills a little faster but remains essentially empty because the first valve is still nearly shut. Open the first valve to the same degree as the second, and the situation changes dramatically. The first valve is doing almost all the work of keeping the tank empty. Closing or opening the second valve is a real but minor effect by comparison. In the dark sky problem, the first valve is finite age, and the second valve is the expansion redshift. Both contribute. The first one overwhelmingly dominates. The quantitative ratio between the two effects can be stated simply. The finite age reduces the total stellar contribution to the sky by a factor of roughly 10 trillion compared to the Olbers result. The additional contribution of expansion, over and above what finite age alone provides, accounts for a factor of only a few times on top of this. The expansion correction is real and measurable, but it is operating on a quantity that is already 13 orders of magnitude below where it would need to be to match Olbers' prediction. The darkness is not fine-tuned by expansion. It is produced decisively by the age constraint, and expansion provides a modest additional reduction. This has an implication that runs in both directions in time. If the sky becomes progressively brighter as the universe ages, because more shells of stars accumulate their contributions, then the sky of the early universe was darker than it is today. A young universe with few stars and a small observable volume would have had a very dim sky in visible wavelengths, with the stellar contribution being a tiny fraction of what it is now. In the first few 100 million years, before the first stars had formed, the stellar contribution to the sky was zero. No star had ignited. No nuclear fusion had begun anywhere in space. Any photons in the sky during that era came from a different source entirely, one that predated stars by hundreds of millions of years and produced not points of light, but a uniform glow filling every direction with equal intensity. That source was not a collection of objects. It was the state of the universe itself. The early universe was hot and dense enough that the matter and radiation in it were in continuous thermal equilibrium throughout all of space simultaneously. The universe did not contain a radiation field. The universe was the radiation field, uniformly bright in every direction, producing a sky that matched Olbers' prediction, not because of infinite shells of stars, but because every point in space was at the same temperature, and every direction was equally luminous. That era lasted for several 100,000 years after the universe began. Then it ended, not gradually, but at a specific threshold, when the temperature dropped far enough for electrons to combine with protons, and the universe shifted from opaque to transparent in a transition that took place throughout all of space within a span of tens of thousands of years. The radiation that existed at that moment streamed outward freely for the first time. It has been traveling in every direction ever since. The expansion has stretched it by a factor of more than 1,000. What began as orange-red thermal radiation has become microwaves, and it fills the sky from every direction with a uniformity that no collection of individual stars could produce. What that light looks like measured precisely, what it tells you about the temperature of the universe when it was released, and how it was found entirely by accident, is where the dark sky paradox opens into something no one expected to find. Olbers was right. He had the wrong universe and the wrong mechanism, but the bright sky he predicted from pure geometry was a real physical state that the universe passed through, every direction glowing with uniform intensity, no dark gaps anywhere, no sight lines that escaped without hitting something luminous. That is an accurate description of the universe for the first several 100,000 years of its existence. The difference is that the source of the brightness was not stars. It was the thermodynamic state of space itself. In the first fractions of a second after the universe began, matter and radiation were so thoroughly mixed that the distinction between them was almost meaningless. The temperature was billions of degrees on the absolute scale. At those temperatures, atomic nuclei cannot hold together, because the thermal energy of individual photons is high enough to break any nuclear bond. Protons and neutrons existed as separate particles in a sea of electrons and photons, all colliding and scattering continuously. A photon in this environment traveled for an extraordinarily short distance before striking an electron and being deflected in a new direction. The distance a photon could travel before its next interaction, what physicists call the mean free path, was smaller than a human hair. The universe was not merely opaque, it was a medium in which light had no direction. It scattered before it could be said to be going anywhere at all. This is what distinguishes the early universe's brightness from anything we can observe today. When we describe a lamp as bright, we mean that it emits photons that travel in a direction, reach our eye, and register as light. In the early plasma, photons were not traveling from a source to an observer. Every point in space was simultaneously absorbing and emitting. The radiation field was in complete thermal equilibrium with the matter. There were no sources and no receivers. There was only a single temperature that described both the matter and the radiation at every location simultaneously. In that state, the concept of a dark region had no physical meaning. A dark region is a place where no light is arriving from any direction. In the early plasma, light was arriving from every direction and from a distance of essentially zero. The first minute of cosmic history saw temperatures fall from billions of degrees to roughly 1 billion degrees, still unimaginably hot, but low enough for a specific process to begin. At around 1 billion degrees, protons and neutrons could stick together without being immediately broken apart by high-energy photons. Nuclear fusion happened not inside a star, but throughout all of space at once. Hydrogen nuclei fused into deuterium, deuterium into helium-3 and helium-4, and tiny amounts of lithium formed at the edges of the reaction chains. By the time the universe had cooled below the threshold for fusion, roughly the first 20 minutes of its existence, the composition of matter was set. Roughly 3/4 of all ordinary matter by mass was hydrogen, and roughly 1/4 was helium-4, with trace amounts of other light elements. That ratio has not changed significantly in the 13 billion years since. The helium in the Sun, in the atmosphere of Jupiter, in the gas of every galaxy, was forged in the first 20 minutes of the universe's life, not in any star, in the universal plasma, before a single star existed. As the universe continued to expand, the temperature continued to fall. At around 100,000 years, the temperature had dropped to tens of thousands of degrees, still far too hot for electrons to stay attached to protons. The matter remained plasma. Photons continued to scatter from free electrons, traveling their tiny mean-free paths before being deflected again. The sky, if there had been an observer, would have looked like being inside a uniformly luminous medium, not a collection of sources, but a continuous glow coming from all directions simultaneously, which is exactly what thermal equilibrium looks like to any point embedded in it. At roughly 380,000 years, the temperature dropped through a critical threshold, somewhere around 3,000 degrees. The energy of individual photons fell below the ionization energy of hydrogen, the energy required to strip an electron away from a proton. Below this threshold, electrons began to remain attached to protons, forming neutral hydrogen atoms that could persist. The effect on the photon mean free path was dramatic. Free electrons scatter photons efficiently. Neutral hydrogen atoms, at the energies relevant to this temperature, do not. As the free electron density dropped, the mean free path of photons jumped from microscopic scales to distances comparable to the entire visible universe. The photons that had been scattering continuously for 380,000 years suddenly found themselves in a transparent medium, free to travel indefinitely without hitting anything. What happened in that transition is captured by the phrase surface of last scattering. Each photon in the early universe had a specific last electron it bounced off before the universe became transparent. That last scattering event is the most recent point in the photon's history before it began its uninterrupted journey. When we detect the oldest photons in the universe, we are not seeing the source that emitted them in any ordinary sense. We are seeing the last electron each photon bounced off at the moment the universe went transparent. Every photon in the cosmic microwave background represents a specific last scattering event that happened at the same cosmic time. Roughly 380,000 years after the universe began, throughout all of space simultaneously. The surface of last scattering is not a surface in the usual sense. It is a shell, centered on us, at a specific distance in time. In the moments after the universe became transparent, the radiation field that had existed in thermal equilibrium throughout the plasma was released. Every photon that had been bouncing around the plasma began traveling freely in whatever direction it happened to be going at the moment of last scattering. For the first time, the universe had a radiation field that was propagating rather than equilibrating. It had the spectrum of a thermal source at about 3,000 degrees, orange-red light the color of cooling embers, and it filled every part of space equally, because the transition to transparency happened throughout all of space at once. The universe after this moment was, for the first time, physically divided into radiation and matter that were no longer in continuous contact. The matter, now mostly neutral hydrogen and helium, continued to cool and clump under gravity. The radiation traveled outward. And in the period immediately following, with the radiation no longer visible bright and no stars having yet formed, the universe entered a phase that has no analog in our current night sky. There was no source of visible light anywhere in the cosmos. The plasma glow had ended. The first stars would not ignite for somewhere between 100 and 200 million years. In the interval, the universe was dark in every electromagnetic band that a human eye or optical telescope could detect, not the partial darkness of a night sky with a few thousand stars. Dark in the way that a sealed room with no sources of any kind is dark. Then, in regions where hydrogen had clumped slightly more densely than average, the gravitational compression became extreme enough to ignite the first fusion reactions in the first stars, and the universe lit up again, this time with individual point sources rather than a uniform glow. The darkness ended, but the darkness's predecessor, the radiation released at recombination, was still traveling in every direction through every part of space. Every point in the universe was being crossed by that ancient radiation continuously. It had been emitted from the last scattering surface and had been traveling unimpeded for the entire subsequent history of the cosmos. It arrived at every location in the universe as a uniform background, indistinguishable in direction. By the time the first stars formed, the radiation had already been traveling for 100 million years. Its temperature had dropped from 3,000 degrees to a few hundred. By the time Earth formed, it had been traveling for 9 billion years, and its temperature was down to a few tens of degrees above absolute zero. It is still traveling now. It has been traveling for 13,800 million years. And the question of whether a signal that ancient, that stretched, that cold, could still be detected. It was detected, and the circumstances of that detection are among the most accidental discoveries in the history of science. The sky is dark because the universe is young. Most shells of stars have not had time to deliver their light. The horizon cuts off the infinite sum before it can accumulate. That answer is correct, but it carries inside it a reversal that the paradox never announced. One that only becomes visible when you ask not just why the sky is dark in visible wavelengths, but what the sky contains. The answer is that the sky is not dark in any fundamental sense. Olbers was right. His prediction of a uniformly bright sky filling every direction came true. It is true right now. The uniform brightness he demanded exists, and it fills the universe from edge to edge, present in every cubic centimeter of space, including the air in this room and the space between the atoms of the body listening to this. The paradox was resolved, and in the resolution, the prediction came true. The geometry that made Olbers' paradox inescapable was that every line of sight, extended far enough into an infinite universe, must terminate on a glowing surface. That geometry is satisfied. Draw a line from your eye in any direction and extend it outward through space. At a distance corresponding to a look-back time of roughly 380,000 years after the universe began, that line reaches the surface of last scattering, the shell from which the oldest photons in the observable universe were released. That surface is uniformly luminous. Every sightline, in every direction, reaches it. It wraps around the observer from every angle simultaneously. The structure of the paradox, the insistence that every direction must be capped by something glowing, is exactly reproduced. The sightlines close, not on individual stars scattered at various distances, but on a single surface that encloses the entire observable universe at a specific moment in time. What the surface of last scattering produces is the cosmic microwave background, a radiation field that fills space with a uniformity that no population of individual sources could replicate. The temperature of the CMB is the same in every direction, to within 1 part in 100,000. That precision is not an approximation or a rough statement. It is a measured fact, verified by instruments sensitive enough to detect temperature differences smaller than 1,000th of a degree. In practical terms, this means that no matter which direction you point a microwave-sensitive detector, you measure the same temperature within that tolerance. The CMB is the closest thing to a perfectly isotropic radiation field that has ever been observed. The only physical system capable of producing it was one in thermal equilibrium with itself, a system where every point was communicating its temperature to every other point rapidly enough to erase any differences. The early plasma was that system. The spectrum of the CMB matches a perfect blackbody curve at a temperature of 2.725 degrees above absolute zero. A blackbody spectrum is what a theoretical ideal emitter produces when it is in thermal equilibrium, a specific mathematical curve that relates the intensity of radiation to wavelength with a peak that depends only on temperature. The early plasma was the closest physical approximation to this theoretical ideal that has ever existed, because it was in genuine thermal equilibrium throughout its entire volume. The CMB, as the fossil of that equilibrium, carries a spectrum that matches the ideal blackbody curve more precisely than any other source in nature. The deviation between the measured CMB spectrum and a perfect theoretical blackbody is smaller than the width of the line on any graph used to show the comparison. The energy carried by the CMB is distributed throughout all of space, and it is not a small quantity. Every cubic centimeter of space in the observable universe contains approximately 411 CMB photons. Not per liter, not per cubic meter, per cubic centimeter. A human body contains on the order of 66,000 cubic centimeters of volume. At any given moment, that body contains somewhere in the range of 27 million CMB photons passing through it, traveling in all directions, each a fossil of the early universe's thermal state. They pass through matter at this temperature without being absorbed because the interaction cross-section between microwave photons and ordinary matter at room temperature is extremely small. The body feels nothing. The photons register on nothing the body contains, but they are there. This is the reversal Olbers paradox contained without announcing it. The paradox asked why the sky was dark. The chain of reasoning built from finite age, expansion, and the observable horizon produced a correct answer to why the visible sky is dark. But the conclusion of that chain brought the full picture to a universe that has a uniformly bright sky from every direction, filling every point in space, arriving at every observer simultaneously from an equal distance in every direction. The sky that Olbers predicted exists. It is just not visible to the eye. The resolution of the paradox and the fulfillment of the prediction that generated the paradox happen at the same time, in the same observation, in the same part of the electromagnetic spectrum. The cosmic microwave background is simultaneously the answer to why the visible sky is dark and the confirmation that Olbers' geometry was satisfied. There is something precise to hold here about what the CMB's uniformity means physically. In the visible sky, no two patches of sky look exactly the same. Stars cluster along the Milky Way. Galaxies clump into filaments and voids. The visible universe has structure at every scale. The CMB has almost none. The tiny variations in its temperature across the sky, at the level of 1 part in 100,000, are not random noise. They are the imprint of quantum fluctuations in the density of the early plasma, the seed variations from which all the structures of the visible universe later grew. The galaxies, the galaxy clusters, the filaments spanning hundreds of millions of light years, all of this structure is the grown-up version of the temperature fluctuations in the CMB. The map of the CMB is literally a baby picture of everything in the universe, taken when the universe was 380,000 years old and projected onto the sky from every direction simultaneously. In the 1940s, Ralph Alpher and Robert Herman calculated that radiation from the early hot phase of the universe should still fill space, and they estimated its current temperature at a few degrees above absolute zero. Their work appeared in published form and was available to the scientific community. It was largely set aside, not refuted, but not pursued. The instruments to detect a signal at a few degrees above absolute zero in the microwave range did not exist in widespread use in astronomical facilities. The theoretical prediction sat in the literature, and the observational capability developed independently of it, in a context that had nothing to do with cosmology. The people who finally detected the CMB were not looking for it. They were troubleshooting an antenna. The signal they found appeared as persistent noise that came from every direction equally and could not be attributed to any known terrestrial or celestial source they could identify. They checked their equipment. They checked their calibrations. They found pigeons nesting in the antenna and removed them and cleaned the installation, and the noise persisted. It did not go away because it was not noise. It was the oldest light in the universe, arriving from every direction at once, indistinguishable from antenna noise because it was completely uniform and had no structure that pointed to a source. The room you are in right now is full of that light, not the metaphorical sense of a room full of history or memory, the physical sense of a room through which CMB photons are traveling in every direction at every moment. The floor, the ceiling, the walls, the air, and the space between every atom of your body are being crossed continuously by radiation that has been traveling since the universe was 380,000 years old. It has been in transit for 13,800,000,000 years. It is everywhere, because it was everywhere when it was released. And expanding space does not create preferred directions that would concentrate it somewhere and leave other places empty. The eye does not see this. The reason it does not involves the same expansion that shaped the whole story of the dark sky and the mechanism by which billions of degrees became 2.725 degrees carries a specific physical logic that closes the question of what the universe is doing with its oldest light. How a temperature of 3,000 degrees becomes a temperature of 2.725, and what that transformation means for the photons that carried it, is the mechanism that makes the invisible sky invisible. The CMB fills space from every direction equally. The eye sees nothing. These two facts are not in contradiction. They describe the same physical situation from two different measurement perspectives, and the gap between them is entirely a property of the detector, not of the radiation. Human vision occupies a narrow slice of the electromagnetic spectrum, roughly between 380 nanometers at the violet end and 700 nanometers at the red end. Below 380 nanometers is ultraviolet light, which the eye cannot detect, but which does interact with skin and causes sunburn. Above 700 nanometers is infrared, which the eye does not see, but which the skin sometimes registers as warmth when the intensity is high enough. The visible range sits between these, a window less than 2 to 1 in wavelength from one edge to the other. In terms of frequency, the entire range of human vision spans slightly less than 1 octave. The electromagnetic spectrum extends over more than 25 octaves in wavelength, from radio waves meters long to gamma rays smaller than an atomic nucleus. The eye responds to less than one of those octaves, The reason this particular octave is the visual range is not coincidental. The sun's output peaks at roughly 550 nanometers, near the center of the visual range. An organism that evolved to detect the most abundant photons in its environment would develop photoreceptors tuned near that peak. Natural selection does not build detectors for radiation that is not present in useful quantities. Eyes are calibrated to starlight from one specific star, and they have been calibrated this way for hundreds of millions of years. The visual range is a biological fossil of the solar spectrum. It tells you something about what wavelengths were common in the environment where eyes evolved, not something about what wavelengths are common in the universe. The CMB occupies a completely different part of the spectrum. Its peak emission falls at a wavelength of roughly 1.5 millimeters, corresponding to a temperature of 2.725 degrees above absolute zero. 1.5 millimeters is about 1.5 million nanometers. The visible range runs from 380 to 700 nanometers. The CMB peak is more than 2,000 times longer in wavelength than the reddest light the eye responds to. There is no mechanism in the human visual system, no photoreceptor, no ion channel, no retinal protein, that is tuned to respond to a photon with a wavelength of millimeters. The CMB photon passes through the eye as completely as if the eye were not there, because at that wavelength, biological tissue is essentially transparent. The analogy that fits most closely is the behavior of sound below the threshold of hearing. A speaker producing a tone at 15 Hz is producing real sound waves. Air molecules are oscillating. Energy is propagating outward from the source. The physics is identical to an audible tone, but the human ear requires a minimum frequency of roughly 20 Hz to detect. And below that threshold, no mechanical process in the ear converts the pressure wave into a neural signal. A tone at 15 Hz can sometimes be felt as a vibration in the chest cavity or perceived as unease or pressure, but it is not heard. The tone exists. The ear is simply not built for it. If you describe the room as silent because you heard nothing at 15 Hz, you would be making a statement about your auditory range, not about what was present in the air. The darkness of the night sky is the same kind of statement. Pointing an eye at the space between stars and registering nothing is measuring the radiation field at wavelengths between 380 and 700 nanometers and finding no significant flux there. The measurement is accurate. The conclusion that the space is therefore empty of radiation is not. The space is full of CMB photons, but they arrive at millimeter wavelengths where the eye has no sensitivity whatsoever. The darkness is an accurate report about what the eye receives. It is not an accurate report about what the space contains. Every cubic centimeter of the room you are in right now contains approximately 400 CMB photons in transit. Your body is being crossed by them continuously. The walls of the room are transparent to them. The materials of the building around you are transparent to them. They pass through everything in the immediate environment without being scattered or absorbed, because the interaction between millimeter wave photons and ordinary room temperature matter is negligible. The body contains no biological structure that registers their presence. They contribute nothing to body heat in any measurable quantity. The only instrument that would reveal them is one designed specifically to detect radiation at millimeter wavelengths, pointed at the sky, isolated from local sources of microwave emission, and calibrated carefully enough to distinguish a signal at 2.725 degrees above absolute zero from thermal noise produced by the instrument itself. Building and operating such an instrument is not trivial. The challenge is not the physics, which is straightforward once the CMB temperature is known and the target wavelength is calculated. The challenge is that the signal is extraordinarily faint and arrives uniformly from every direction, which means it cannot be distinguished from the thermal emission of the detector itself by looking for a localized source. A detector at room temperature generates more thermal microwave noise than the signal it is trying to measure. Cooling the detector to near absolute zero reduces its own thermal emission and lets the signal emerge. When an instrument sensitive to this range of the spectrum is pointed at any part of the sky away from obvious local sources, it registers a uniform signal consistent with a blackbody at 2.725 degrees. The sky in that instrument's view is not dark. It is uniformly and brightly luminous, wrapped around the observer from every direction, exactly as Olbers' geometry demanded. The version of the sky that appears dark is the version visible to eyes evolved for one particular star. The version visible to an instrument built for the residue of the early universe looks completely different. The people who first saw that version of the sky were not looking for it, and their discovery of it began with a noise they could not explain and a nest of pigeons they removed from an antenna that was picking up the beginning of the universe. In 1964, Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey, with a very specific and practical goal. They had been given access to a large horn-shaped radio antenna that had been built in 1959 for the ECHO satellite program, an early experiment in bouncing radio signals off a reflective balloon in orbit to relay communications across the country. The satellite work was over, and the antenna was available. Penzias and Wilson wanted to use it to measure radio emission from our own galaxy, a legitimate and useful astronomical project. To do accurate astronomy with any radio antenna, you first need to understand every source of noise in the system. The antenna itself generates some noise from thermal emission. The electronics generate noise. The sky generates noise. Before you can measure a faint signal, you have to account for everything you are not trying to measure. This calibration work is unglamorous and methodical, and Penzias and Wilson were doing it carefully. What they found was a persistent excess noise that came from every direction equally, day and night, through all seasons, regardless of which way the antenna pointed. It was equivalent to the antenna picking up radiation from a source at a temperature of roughly 3.5 degrees above absolute zero, everywhere and always, with no variation and no identifiable origin. They worked through every possibility. They checked all the electronics. They measured the noise from the antenna's own materials. They recalibrated. They found that pigeons had been roosting inside the antenna and had left what their subsequent paper described, in one of the more genteel phrases in the scientific literature, as a white dielectric material coating the interior surfaces. They removed the pigeons, sent them to another location, cleaned the antenna thoroughly, and measured again. The signal remained. The excess was real. It was not going away. What Penzias and Wilson did not know at the time was that 60 miles away at Princeton University, a physicist named Robert Dicke had independently derived the theoretical expectation for exactly this kind of signal. Dicke had concluded that radiation from the early hot phase of the universe should still fill space at a temperature of a few degrees above absolute zero, and he had assembled a team to build a detector to look for it. His group was in the process of constructing that detector when Penzias, having heard from a colleague about Dicke's theoretical work, called Princeton. Dicke took the call, listened to the description of the unexplained excess signal, and reportedly turned to his research team when he hung up and told them, in a phrase that has been quoted in cosmological histories ever since, that they had been scooped. The two groups published back-to-back papers in the Astrophysical Journal in 1965. Penzias and Wilson described the detection of an anomalous excess antenna temperature. Dicke and his colleagues provided the cosmological interpretation. What Penzias and Wilson had found was the cosmic microwave background, the fossil radiation from the moment the universe became transparent, predicted in general terms by Ralph Alpher and Robert Herman in the 1940s, rederived by Dicke independently, and now confirmed by an accidental measurement at a communications facility in New Jersey. The steady-state theory, which had been proposed by Fred Hoyle and colleagues as an alternative to the Big Bang model and which predicted no such background radiation, could not accommodate the discovery. A universe in a steady state would have no epoch of extreme heat and density from which a thermal background could emerge. The CMB was direct evidence of a past state that the steady-state model did not allow. The debate between the two cosmological models, which had been ongoing since the 1940s, effectively ended, not by philosophical argument or mathematical elegance, but by a signal that arrived from every direction and could not be made to go away. There is a detail about the CMB that places it closer to ordinary human experience than any other relic of the early universe. Analog television sets, the kind that used cathode ray tubes and required tuning with a dial or a knob, displayed visual noise on untuned channels, the flickering black and white static that appeared when the receiver was not locked onto any broadcast signal. That static was produced by thermal noise in the electronics, random radio frequency interference from the environment, and a small but real contribution from the cosmic microwave background itself. The fraction was small, probably around 1 to 2% of the total static on a typical set, depending on the receiver's frequency range and sensitivity. But for the decades between the introduction of broadcast television and the digital transition, which moved most television signals to cable or digital satellite, people watching static on untuned sets in living rooms around the world were seeing, mixed into the random flicker, a contribution from the oldest light in the observable universe. They were watching ancient photons without knowing it. Penzias and Wilson received the Nobel Prize in Physics in 1978 for the discovery. Robert Dicke did not, which has been noted by historians of science as a case where the distinction between theoretical prediction and observational confirmation produced an outcome that not everyone found entirely satisfying. The Nobel Committee's decision reflected a long-standing tradition of favoring experimental results over theoretical frameworks in the citation. Whatever the merits of that tradition in this case, the practical consequence was that the two men who stumbled on the CMB while troubleshooting a noise problem received the highest recognition in physics, while the man who had predicted what they found and was building an instrument to look for it did not. Science does not always distribute its rewards with the neatness that a history of ideas would suggest. What the detection established is now the observational foundation of modern cosmology. The CMB confirmed that the universe began in a state of extreme heat and density, that this state was uniform to high precision across the observable universe, and that the universe has been expanding and cooling continuously since. Subsequent measurements refined the temperature from Penzias and Wilson's initial estimate of roughly 3.5 degrees to the current value of 2.725 degrees, and detailed maps of tiny variations in the CMB temperature across the sky have become one of the primary tools for measuring the parameters of the universe, including its age, its composition, and the amplitude of the density fluctuations that eventually became galaxies. The CMB has been crossing this room throughout this entire conversation. It was crossing the room before this building existed. It was crossing this region of space before the Earth formed, before the Sun ignited, before the Milky Way had its current shape. The photons that constitute it were released when the universe was 380,000 years old and have been traveling in every direction without interruption since. There is nowhere in the observable universe where the CMB is absent, because there is nowhere that was not inside the early plasma when the transition to transparency occurred. Every location in space was simultaneously the source and the receiver of that radiation when it was released. Every location has been a receiver of it from every direction since. The body lying here in the dark is inside the oldest uniform radiation field in the universe, bathed in it without perceiving it, the way a fish is bathed in water without having a particular concept of wetness. The discovery of the CMB was a detection of a surface in time, the last moment when the universe was opaque, the first moment when light could travel. What that surface looks like in detail, what its structure reveals about the conditions in the universe before any star existed, and how it serves as a starting point for every structure in the visible cosmos, is what the signal carries once you know how to read it. The CMB is the oldest map there is, and the features on that map were not put there by anything that had yet formed. They were there before stars, before galaxies, before any complexity existed anywhere. The cosmic microwave background does not come from a place. It comes from a moment. Every photon in the CMB carries a timestamp, the instant of its last interaction with the early plasma, somewhere around 380,000 years after the universe began, and that timestamp is the same for every CMB photon in every direction. The surface of last scattering is not a shell in space the way the surface of a distant planet is a surface in space. It is a shell in time, a particular moment that encloses the observable universe. And because the speed of light connects distance and time in a fixed ratio, looking outward in any direction to the right distance is equivalent to looking backward to that same moment. Every sightline in every direction reaches the same epoch. The CMB arrives from everywhere because everywhere was at the same moment of transition simultaneously. This creates an observational limit that is not merely practical, it is physical, and it has a specific character. Before recombination, the universe was opaque to photons, not faintly transparent, not poorly lit, but completely impenetrable in the sense that a photon emitted by any process before that transition would scatter from a free electron within a distance smaller than an atom, absorb back into the plasma, and re-emerge in a random direction. Information about the state of the universe during those first 380,000 years did not escape. Any telescope, however large, any detector, however sensitive, operating at any electromagnetic wavelength, is reading from a book whose first 380,000 pages have been removed, not lost, not faded, but prevented from carrying any signal to outside observers. The CMB is not an image of the early universe in the usual sense. It is the cover of a book whose interior cannot be read by any photon-based instrument. The analogy that fits most precisely is the sun's photosphere. Looking at the sun in visible light, you see a surface. Not a solid surface in the way a rock is solid, but a layer of plasma at about 6,000 degrees where the sun's interior transitions from opaque to nearly transparent. Everything below that layer is hidden: the nuclear reactions in the solar core, the convective motions in the intermediate layers, the magnetic field structure deep in the interior. All of this is invisible to optical instruments because the photons generated inside the sun scatter before they can travel far enough outward to escape. The only way to probe the solar interior directly is through particles and waves that interact more weakly with matter than photons do. Neutrinos, for instance, stream outward from the nuclear reactions in the solar core and pass through the overlying plasma without scattering, carrying information about the core to detectors here on Earth. Helioseismology, the study of acoustic oscillations propagating through the solar interior, provides another indirect window. The same two methods that allow access past the solar photosphere also, in principle, allow access past the cosmic photospheric wall. Neutrinos decoupled from matter in the early universe at about 1 second after the Big Bang, when the universe was still approximately 10 billion degrees. Before decoupling, they were in thermal equilibrium with everything else. After decoupling, they streamed freely in every direction, like the CMB photons would do later. A cosmic neutrino background, analogous to the CMB, should fill the universe at a temperature of roughly 1.95 degrees above absolute zero, slightly colder than the CMB because neutrinos decoupled slightly earlier and have been cooling for slightly longer. This background has not been directly detected. Neutrinos interact so weakly with matter that detecting a thermal background at 2 degrees is far beyond the current capability of any neutrino detector. But the neutrino background's existence is confirmed indirectly through its effects on the early plasma and on the CMB spectrum. It was present. It is still present. It carries information about the state of the universe at 1 second, 380,000 years before the CMB photons were released, and it is passing through this room along with everything else. Gravitational waves provide an even earlier potential window. If the period of rapid expansion called inflation occurred in the very early universe, it would have produced a background of gravitational waves, ripples in space-time that propagate at the speed of light but interact negligibly with matter. Such a background would carry information about conditions in the first tiny fraction of a second. No primordial gravitational wave background has been directly detected yet. The signal is expected to be extraordinarily faint, and the current generation of gravitational wave detectors is not sensitive enough to measure it. Future space-based detectors may open that window. If it is ever opened, it would allow observation of an era more than 100,000 times earlier in cosmic history than the CMB. The CMB itself contains more information than its average temperature suggests. The tiny variations in temperature across the sky, at the level of 1 part in 100,000, encode the pattern of density fluctuations in the early plasma at the moment of recombination. These were the seeds of all subsequent structure. Before recombination, the plasma supported acoustic oscillations, pressure waves propagating at roughly 57% of the speed of light through the coupled matter radiation fluid. These were real sound waves, in the literal sense of alternating compressions and rarefactions moving through a medium, just as sound moves through air. When recombination happened and the photons decoupled, these waves were frozen in place. The characteristic scale of the largest such oscillation, roughly 980 million light-years in current distance units, is imprinted on the CMB as a specific angular scale and on the distribution of galaxies as a preferred separation distance. This feature is called the Baryon Acoustic Oscillation Scale, and measuring it in both the CMB and the galaxy distribution allows precise determination of the universe's geometry and expansion history. The pattern of temperature fluctuations in the CMB has been mapped with increasing precision by a series of satellite missions. The COBE satellite in the 1990s detected the fluctuations for the first time. WMAP in the 2000s mapped them with significantly higher resolution. The Planck satellite, operating from 2009 to 2013, produced the most detailed map of the CMB ever made. The temperature fluctuations in the Planck map, at the level of tens of millionths of a degree on angular scales down to a fraction of a degree, match the predictions of the standard cosmological model with remarkable precision. The same expansion that was inferred from the recession of galaxies, the same age that was calculated from the Hubble constant, the same composition of dark matter and dark energy that other observations suggest, all of these are confirmed independently and simultaneously by fitting the detailed pattern of CMB temperature fluctuations. The CMB is not merely consistent with the Big Bang model, it is the most powerful single piece of evidence for it. The photons of the CMB carry information only about the moment they were released and about everything between that moment and the present that they traversed on their way to any given observer. They cannot carry information about what happened before their last scattering event. The universe that existed during the first 380,000 years is not directly visible in any photon-based observation. It is inferred from what came out of it, the composition of the light elements, the temperature and spectrum of the CMB, the distribution of baryon acoustic oscillations. These are all consequences of the conditions during the opaque era, readable in the fossils that survived, but not directly observable in the thing itself. What the CMB establishes beyond question is that the universe expanded from a hot, dense state. The expansion is not an inference from the recession of galaxies alone. It is required by the existence of the CMB at the temperature it has, with the spectrum it has, arriving from the direction it does, with the fluctuations it carries. The expansion and the CMB are two independent observations of the same physical history, and they agree. For decades, though, an alternative explanation for the recession of galaxies existed that did not require the universe to be expanding at all, and that alternative would have made very different predictions about what a thermal background from the early universe should look like. Whether light could simply grow tired on long journeys, losing energy without any stretching of space, was a question that was taken seriously long enough to require a specific and careful refutation. The year before Edwin Hubble published his evidence for expanding galaxies, a Swiss physicist named Fritz Zwicky proposed an alternative explanation for why distant galaxies looked redder than nearby ones. He suggested that photons lose energy as they travel through space, not because the space is stretching, but because of some interaction between the photon and whatever it passes through on its long journey. Energy loss means lower frequency. Lower frequency means longer wavelength. A photon that started its journey as blue light could arrive red, without the universe having expanded at all. Zwicky called this hypothesis tired light. It was a provocative idea from a scientist who made a habit of them. In the same decade, Zwicky would propose dark matter, predict neutron stars, and develop the concept of galaxy clusters as gravitational lenses. Not all of his proposals were right, but none were careless. The tired light paper was a serious attempt to explain the observations without requiring the universe to have a beginning, and it appealed to other scientists who found the implications of an expanding universe philosophically uncomfortable. The appeal was not irrational. An expanding universe had to be explained. If everything is moving apart now, what set it in motion, and what was the universe doing before it started? An eternal, static universe had no such questions attached to it. Matter was there, space was there. Light traveled through it all, and the redshift of distant galaxies was simply a consequence of the light's long journey, rather than a statement about the history of space itself. The hypothesis was clean in concept, required no dramatic origin event, and did not demand any revision of the basic picture of a cosmos that had always been essentially as it is now. The problem with the proposal was that the mechanism behind it remained unspecified. Zwicky did not identify a known physical process that would cause photons to lose energy in proportion to distance. He gestured at interactions with intergalactic matter, with other photons, with some property of space that had not yet been measured. Different physicists who later took up the idea proposed different mechanisms. Photons scattering off intergalactic gas, photons interacting with hypothetical particles, photons losing energy to a pervasive medium of some kind. None of these proposals connected cleanly to established physics. A pebble thrown through air slows down because of friction with the molecules of the gas, a well-understood collision process that transfers kinetic energy from the pebble to the air. Something equivalent would need to exist for photons. In a vacuum, photons travel at a fixed speed without losing energy, and no deviation from this has ever been measured at any scale or energy. A mechanism that would cause photons to lose energy in proportion to distance traveled would have a specific signature beyond the energy loss itself. Energy is not the only thing that changes when photons interact with matter. Their direction changes too. Scattering redistributes photon trajectories, blurring the image of any source seen through a scattering medium. Fog blurs distant lights, not just because it absorbs some of the light, but because it redirects what it scatters in random directions. Any physical process capable of draining a photon's energy over billions of years of travel would produce a corresponding angular scattering, and that scattering would make distant objects appear fuzzy beyond what any point-spread function of a telescope could account for. The most distant galaxies observed with modern instruments are sharp as local galaxies modulo, the limits of the optics and the distance dimming. The predicted blurring from any energy-losing scattering process is not there. The more definitive test came from supernovae, a type Ia supernova, a specific category of stellar explosion produced when a white dwarf accumulates mass beyond a critical threshold, has a characteristic light curve. It brightens to a peak over roughly 3 weeks and then fades over the following months, following a distinctive time profile. Because this time profile is the same for all type Ia supernovae, it serves as a clock. In an expanding universe, a supernova at high redshift should have both its light wavelengths and its timescale stretched by the expansion factor. A supernova at a redshift of 1, where the universe has expanded by a factor of 2 since the light was emitted, should have a light curve that peaks and fades at twice the rate of a local supernova. The light curve is time-dilated. In a tired light universe, the expansion never happened. The wavelengths are redshifted by the energy loss mechanism, but the time scale of the explosion itself is not affected. A supernova at redshift 1 would brighten and fade at the same rate as a local one. When astronomers measured high redshift type Ia supernovae in the 1990s and into the 2000s, the light curves were time-dilated. The supernovae at higher redshifts took longer to complete their light curves by exactly the factor that expansion predicts. The time stretching and the wavelength stretching were consistent with the same expansion factor. Tired light predicts no time stretching and so cannot accommodate the observations. The measurements that produced this result came primarily from the Supernova Cosmology Project and the High-Z Supernova Search Team, the same measurements that led to the discovery of the accelerating expansion and the 2011 Nobel Prize in Physics. The tired light hypothesis was not the target of those measurements, but it was one of the alternatives definitively ruled out by them. The CMB provides a second and independent refutation, a thermal background at 2.725 degrees above absolute zero, with a spectrum matching a perfect blackbody to the precision measured by COBE and subsequent missions, is what expansion predicts. In an expanding universe, the early plasma was in thermal equilibrium, and the radiation it released was thermal radiation. Thermal equilibrium produces a blackbody spectrum, and expansion shifts a blackbody spectrum to lower temperatures while preserving its shape. A blackbody spectrum shifted to 2.725 degrees is still a blackbody spectrum. What tired light would predict is different. Any process that caused photons to lose energy in proportion to distance traveled would affect photons of different initial energies differently, unless the mechanism were extraordinarily precisely tuned to produce exactly the same fractional energy loss per unit distance, regardless of photon energy. No known physical process has this property. Without it, the different wavelengths of the CMB would be shifted by different amounts, distorting the blackbody spectrum into something else. The CMB spectrum, as measured, is the most precise blackbody spectrum ever recorded. The distortion that tired light mechanisms would produce is absent. A tired light universe would have a CMB that looked different from what we observe, and the difference is large enough to have been detected. What the failure of tired light demonstrates is something about how alternatives to established models get tested. An alternative to expansion was proposed, was debated for decades, and was eventually confronted with specific predictions that it could not meet. The time dilation of supernova light curves is a test that requires only measuring the duration of events at high redshift and comparing to local events. The CMB blackbody spectrum is a test that requires measuring the spectrum of the background radiation with high precision. Both tests were eventually done with sufficient precision to give a clear answer, and both answers were inconsistent with tired light and consistent with expansion. The tired light alternative was not dismissed on philosophical grounds. It was refuted by the same kind of observational comparison that established the expanding universe in the first place. Zwicky's lasting contributions to astronomy were considerable. His tired light proposal was not among them in terms of final standing, but it was not a negligible contribution either. It kept the expanding universe from being accepted on grounds that were not sufficiently tested, and the effort to refute it built the methods that later produced the supernova measurements. Science progresses partly through the effort required to demonstrate conclusively that a serious alternative does not work. With expansion confirmed by multiple independent methods, the logic of running it backward is secure. A universe expanding now was smaller in the past, small and hot, before any stars had formed. And in that hot early universe, for hundreds of millions of years after the plasma cleared, no star had yet ignited anywhere. What that era of true universal darkness looked like, and what ended it, is where the thread from the dark sky question finally closes on the birth of the first light sources. There was one era in cosmic history when the sky was dark in the specific, literal sense that Olbers' paradox demanded. The darkness was not the darkness of finite age, where most stars are too far away for their light to arrive. The darkness was not the darkness of expansion, where photons drain of energy en route. The darkness was the darkness of nothing shining anywhere. Every sightline in every direction ended on nothing, not on a distant star, not on a glowing plasma surface, not on any source of radiation at visible wavelengths. For several hundred million years after the universe became transparent, the cosmos was a place without light sources. The CMB had faded to microwave wavelengths, invisible to any biological eye and emitting less energy per photon than anything that could drive a chemical reaction. The neutral hydrogen and helium that made up almost all ordinary matter sat in the dark, cooling, settling, drifting slowly together under the one force that still acted without a countervailing pressure. The universe was dark, and it was quiet, and it was patient. This era carries a name in cosmology: the Dark Ages. Its onset is well defined as the moment of recombination, roughly 380,000 years after the Big Bang, when the plasma went transparent and the CMB was released. Its end is less precisely fixed because it did not end at once across the whole universe, but gradually, in patches, as the first sources of light appeared and then multiplied. The best current estimates place the first stars somewhere between 100 million and 400 million years after the Big Bang, with the uncertainty reflecting how difficult it is to observe an era that produced so little light and how sensitive the timing is to conditions we cannot yet measure directly. During the Dark Ages, the universe was transparent for the first time in its history. The recombination transition had converted the opaque plasma into neutral gas, and neutral hydrogen at low temperatures is nearly invisible. Light, had there been any, could have traveled for billions of light years without encountering significant absorption. But there was no light to travel. The universe was simultaneously transparent and dark in a way that has no parallel in ordinary experience. A clear night sky is dark between the stars but filled with starlight. A cloudy night is dark and opaque. The Dark Ages universe was dark and transparent, the combination that a vacuum produces when there is no source anywhere to emit. The temperature of the neutral hydrogen fell continuously during this period. At recombination, it was roughly 3,000 degrees. Within tens of millions of years, it had fallen to a few hundred degrees, cooled by the expansion. By the time the first stars were approaching formation, the gas temperature in most of the universe was only a few tens of degrees above absolute zero. The CMB itself, still present in the microwave range, bathed the neutral hydrogen in a faint background of radiation, and the hydrogen temperature gradually coupled to and then slightly fell below the CMB temperature as the universe expanded and the two decoupled from each other. This process of cooling and decoupling left a specific signature in the behavior of the hydrogen atoms, a quantum transition that neutral hydrogen undergoes between two closely spaced energy states, separated by the energy corresponding to a photon with a wavelength of 21 centimeters. During the Dark Ages and the subsequent epoch of reionization, this transition was occurring throughout the universe, producing radio wavelength emission and absorption that encodes the thermal and structural state of the hydrogen gas at different epochs. Detecting this 21-centimeter signal from the Dark Ages is one of the observational frontiers of modern cosmology. The signal has been redshifted by the expansion to wavelengths of several meters by the time it reaches us, placing it in the radio frequency range accessible to very large antenna arrays. Ground-based experiments, including the experiment to detect the global epoch of reionization signature and the hydrogen epoch of reionization array, are attempting to measure the global signature of this era. The signals are faint and sit in a frequency range crowded with radio frequency interference from human technology, making the detection extraordinarily challenging. A tentative signal consistent with the Dark Ages hydrogen absorption was reported in 2018 and remains under active investigation. If confirmed, it would represent the first direct measurement of conditions during this era. In the regions of slightly higher density that had been seeded by the quantum fluctuations of the early plasma, gravity was slowly winning. Dark matter, which interacts only through gravity and does not emit radiation, had been clumping since before recombination and had established a network of filaments and halos by the time the neutral hydrogen decoupled. The neutral gas followed this scaffolding, accumulating in the densest regions where dark matter halos had formed. Over millions of years, the densest gas clouds contracted further. As they contracted, the gas pressure increased. As pressure increased, so did temperature. The compression was working against gravity's pull, and for a long time the gas found an equilibrium where pressure balanced infall. Then, in the very densest regions, the temperature rose high enough and the density rose high enough that hydrogen nuclei could begin to fuse. The first star ignited in the dark. The specific moment and location cannot be known, and the first star has never been directly observed, but the physics of what it was like is well constrained. These first stars, which cosmologists call population 3 stars, formed from gas that contained only hydrogen, helium, and trace amounts of lithium, the elements produced in the first 20 minutes. Without heavier elements to radiate heat and help the gas cool, the clouds that collapsed were more massive and hotter than typical star-forming regions today. Population 3 stars were likely far more massive than the Sun, perhaps hundreds of times more massive in some cases. They burned hotter, brighter, and faster. A star 100 times more massive than the Sun might exhaust its nuclear fuel in 1,000,000 years, compared to the Sun's 10 billion-year lifetime. They were brilliant for their brief existence, and then they died, and in dying they produced the first heavy elements beyond lithium. The ultraviolet radiation from the first stars began a process that gradually transformed the universe again. Ultraviolet photons have enough energy to strip electrons from neutral hydrogen, converting neutral gas back into plasma. Around each early star, a bubble of ionized gas expanded outward through the surrounding neutral medium. As more stars formed, more bubbles appeared, and the bubbles expanded and merged. This process, called the epoch of reionization, converted the universe from a sea of neutral hydrogen to an ionized plasma again, though in a very different state from the early plasma, tenuous, cool, and riddled with the growing structures of galaxies and clusters rather than uniformly dense and hot. The Dark Ages ended not when the first star ignited, but when enough stars existed that the darkness between them was significantly less total than it had been. That process took hundreds of millions of years and was not complete until somewhere around 1 billion years after the Big Bang. The universe had been dark, in the sense of containing no visible light sources anywhere, for a span of time roughly 10 times the age of the Earth. This is the context in which the current dark sky exists. The darkness outside the stars today is the continuation of the darkness of the Dark Ages, modified by the finite light that has arrived in the time since stars began to burn. The Olbers' satisfying darkness was real. It has been partially but not fully replaced. Whether the stars that eventually formed, sparse and distributed as they are through the enormous volume of space, could ever collectively overcome that original dark, even given all the time the universe had to offer, is the question the geometry of sightlines and shells was always pointing toward. The first stars could not fill the sky. Even billions more of them, spread across billions of years of the universe's history, produced only the specific level of brightness that the dark sky holds tonight. Think back to the forest image, the one where every horizontal sightline terminates on a trunk in an infinite, uniformly populated forest with no direction left open to look out through. That is the forest Olbers paradox demands, and it was used to show why an infinite, eternal, uniformly populated universe should produce a bright sky. The universe that emerged from the Dark Ages was the opposite of that forest. It was a young forest where the trees had just appeared, where the spaces between them were thousands of times wider than the trees themselves, where most horizontal lines of sight passed between every trunk in view and extended to open space beyond. A traveler in that forest would have no trouble seeing through it. The trees were real and some of them were enormous, but the gaps between them were so vast that the forest barely registered as an enclosure. Most directions were open. The first stars were not distributed through space the way the trees in Olbers' imagined forest were distributed. They formed in isolated clumps, in the densest halos of dark matter that had assembled during the Dark Ages, and these halos were separated from each other by distances measured in millions of light years. Between halos, there was neutral hydrogen slowly being ionized, dark matter in its less dense configurations, and the CMB at its still cooling microwave frequency. No star occupied those intergalactic corridors. A sightline extended from any point in the early universe had to travel millions of light-years before it had a reasonable chance of finding a star at the far end. Most sightlines passed through nothing for their entire length, which in those early times was limited to a fraction of what is now the observable universe. The inverse square law is unforgiving at these separations. A star 100 times more massive than the Sun is roughly 1,000,000 times more luminous, an extreme object by modern standards. At a distance of 1,000,000 light-years, which was a typical separation between the first star-forming halos, that star delivers less than 1,000,000th of 1,000,000th of the energy that our own Sun delivers to Earth. The brightness falls with the square of the distance, and 1,000,000 light-years is roughly 400 million times the distance from Earth to the Sun. The square of 400 million is a number with 17 digits. The most luminous population 3 star, sitting 1,000,000 light-years away, delivered a contribution to the sky brightness that was negligible by any measure a biological eye could register. There is a further problem beyond the separation. The first stars did not last. A massive star burns through its nuclear fuel at a rate that scales steeply with mass. A star 100 times more massive than the Sun exhausts its core hydrogen in roughly 1 to 3 million years. For comparison, the Sun has been burning for about 4.5 billion years and has perhaps another 5 billion remaining. The first stars were brief. They ignited, blazed, and died in explosions that scattered their newly forged heavy elements into the surrounding gas. Then they were gone. The halos that hosted them were left with hot, metal-enriched gas from which the next generation of stars would eventually form. But the specific bright source that had existed was extinguished. The forest was not just sparse. The trees fell before the sightlines could accumulate much light from them. What the numbers say about the early universe's sky brightness is striking even by comparison to the analysis of the current sky. The shell argument, applied to the observable universe of that era, shows that the volume of space from which starlight had had time to arrive was a tiny fraction of what it is today. At 100 million years after the Big Bang, the light travel time available was 100 million years, not 13,800,000,000 years. The observable volume at that moment was roughly 17,000 times smaller in radius and nearly 5 trillion times smaller in volume than the observable universe today. The accumulated starlight from such a small observable volume, with the sparse, brief first stars scattered through it, was negligible against any standard except the absolute zero of the Dark Ages. The generations of stars that followed were different. With heavy elements now present in the gas, the cooling that allows gas clouds to fragment into smaller, less massive stars became possible. Population 2 stars, formed from slightly enriched gas, were more like the stars we see today, smaller and longer-lived. Then population I stars, formed from gas that had been recycled through multiple stellar generations, including the Sun. Each generation contributed to the slow brightening of the sky. Each generation left more stars alive at any given moment than the previous one, because longer-lived stars accumulate over time even as new ones form. The stellar density integrated over the observable volume has been growing for 13 billion years. The sky of 10 billion years ago was darker than the sky of 5 billion years ago, which was darker than the sky of today. But the accumulated brightness of all this stellar history, summed across the entire observable universe across the entire history of star formation, still falls roughly 10 trillion times short of the Olbers prediction. The reason connects to the forest image in a precise way. Even accounting for every star and every galaxy that has ever burned in the observable universe, the average density of stars through space is still far too low for every sightline to terminate on a stellar surface. The observable universe contains roughly 2 trillion galaxies, each containing hundreds of billions of stars on average. Yet the total solid angle covered by all of those stellar surfaces, if you spread them across the full celestial sphere, covers only a tiny fraction of the sky. The gaps between them are vast. The forest is still mostly open space. The distribution of stars also works against filling the sky uniformly. Stars are not spread through space the way dust is spread through a room. They are congregated in galaxies. Galaxies are congregated in groups and clusters. And between the clusters of galaxies lie enormous voids, regions hundreds of millions of light years across in which no galaxy resides. A sightline aimed into one of these voids extends for hundreds of millions of light years without encountering any star or galaxy. It eventually reaches a wall of the void, a region where galaxies cluster at the void's boundary, but by that point, the inverse square dimming of the galaxies on the far wall has reduced their contribution dramatically. The large-scale structure of the universe creates regions of concentrated light and vast regions of almost none, and the average is far below Olbers level. The forest analogy comes full circle here. In the Olbers forest, every tree is within a few meters. In the actual universe, the typical distance to the nearest galaxy is several million light years. And to the nearest star not in our own galaxy, it is about 4 light years only, because we happen to live inside one. The universe from outside any galaxy looks like the sparsely treed young forest, with most directions clear. The difference from Olbers' dense, infinite forest is not a matter of how the mathematics works. The math was correct. The difference is that the physical conditions necessary for the math to apply, infinite stars with infinite time to deliver their light, have never been met. The actual forest has finite trees, finite time, and a distribution that leaves most directions open. The sky has been brightening since the first stars formed, and it will continue to brighten as long as new stars are forming and contributing their light within the observable horizon. But the rate of star formation in the universe peaked roughly 10 billion years ago and has been declining since. The universe is making fewer new stars per year now than it was making then. The sky's brightness growth is slowing. At current rates, the sky will never reach Olbers' brightness on any timescale relevant to the remaining life of the universe's star-forming capacity. What the sky is doing now, and whether the darkness is holding steady or shifting under forces that are still accumulating. The darkness of today's sky is not a fixed condition. It is a moment in a history that is still moving, and the direction it is moving is not toward brightness. Walk into a dark room and stand still. For the first few seconds, the room seems black. Then, gradually, shapes emerge. The chair by the wall, the outline of the window, the faint rectangle of light under the door. Your visual system is adapting. Your pupils are widening, and the rod cells in your retina are increasing their chemical sensitivity to the photons that were present all along but too sparse to register. The room was never as dark as it first appeared. The night sky works the same way, scaled up and made more complex. What appears to be a black field punctuated by bright points is, on closer measurement, a field with a background brightness that is never zero. Even in the most remote location on Earth, far from any city or settlement, under a sky that professional astronomers describe as excellent, the night sky between the visible stars carries a diffuse glow from multiple overlapping sources, each invisible on its own, collectively preventing the sky from ever reaching true black. The first and most pervasive of these sources is the atmosphere itself. The air around the Earth does not simply transmit starlight or scatter it. It emits light at night through a process called airglow. During the daytime, solar ultraviolet radiation drives chemical reactions in the upper atmosphere, creating excited atoms and molecules that store energy in unstable electronic states. After sunset, when the direct solar input stops, these unstable states release their stored energy as photons. Atomic oxygen produces airglow at a wavelength of 557.7 nanometers in the green portion of the visible spectrum. Hydroxyl radicals, produced by reactions between ozone and hydrogen, emit strongly in the near-infrared. Sodium atoms in the mesosphere contribute a faint yellow-orange emission. The result is a sky that, even at zenith on a moonless night far from any artificial light source, glows faintly from above. The specific wavelength of the atomic oxygen emission, 557.7 nanometers, falls near the peak sensitivity of the human eye in low-light conditions. Long-exposure photographs taken at dark astronomical sites routinely show the sky tinged faintly green, a color that the eye itself rarely notices directly, but that cameras and spectrometers confirm is real and measurable. Airglow is not constant. It pulses with waves driven by atmospheric gravity waves, brightens and dims on timescales of minutes to hours, and responds to solar activity over the 11-year cycle. A night sky that appears perfectly dark and uniform to the eye is rippling with faint structure in the airglow layer at an altitude of roughly 90 kilometers. The second source is not atmospheric but solar. The inner solar system contains an enormous population of dust particles, ranging from microscopic grains to larger fragments, scattered along the plane of the orbits of the planets. This interplanetary dust is too dilute to be visible as a solid medium, but when sunlight strikes it, each particle scatters a fraction of that light in all directions. The cumulative scattering from all these particles produces the zodiacal light, a faint pyramid of illumination that extends from the horizon in the direction of the sun and can be seen with the naked eye from dark locations in the hours after evening twilight or before dawn. A subtler extension of the same phenomenon, called the zodiacal band, spreads across the entire sky along the ecliptic, and a faint brightening in the direction directly opposite the sun, called the Gegenschein, marks the backscatter direction. The zodiacal contribution to the sky background is comparable in magnitude to the contribution from the stars of the Milky Way themselves. Starlight is the third contributor, not from any individual star, but from the aggregate of all stars, too faint to appear as distinct points to the naked eye, contributing their light collectively to a diffuse background that spreads across the entire sky. Our galaxy contains a few 100 billion stars, the vast majority of which are individually invisible to unaided human vision. But they are not contributing zero to the sky brightness. Their light travels to us, too faint per star to see as a point, but summed across all of them producing a measurable diffuse glow. Away from the bright band of the Milky Way, where the density of stars is highest, this integrated starlight still contributes a significant fraction of the sky background, mixed with light scattered from dust within our galaxy, that amplifies the diffuse glow further. Astronomers measure sky brightness in a unit called magnitudes per square arcsecond, a scale where larger numbers indicate fainter surfaces. At the darkest natural locations on Earth, the sky background at the zenith, in the middle of the night, away from the Milky Way band, measures around 22 magnitudes per square arcsecond. This is an enormously faint surface brightness, far beyond what the eye can analyze consciously, but it is measurable with sensitive instruments, and it is definitively not zero. On this scale, the sky at a typical suburban location might measure 18 or 19 magnitudes per square arcsecond. The difference between a dark sky and an urban sky is real and significant for astronomical observation. But even the dark sky has a floor set by airglow, zodiacal light, and integrated starlight. The practical significance of this floor becomes clear when you try to measure something much fainter, specifically the cosmic optical background, the accumulated diffuse glow from all galaxies in the observable universe beyond our own. The cosmic optical background is roughly 1,000 times fainter than the sky background at the darkest natural Earth location. It is buried under the local contributions so completely that no ground-based telescope can extract it directly. Measuring it requires removing the airglow by going above the atmosphere. Removing or characterizing the zodiacal light requires either going far enough from the inner solar system that the dust density drops dramatically, or modeling it with sufficient precision that it can be subtracted from the total measurement, and then accounting for diffuse galactic light, diffuse background contributions from faint, unresolved sources within our own galaxy. Every time astronomers have attempted to measure the cosmic optical background from Earth orbit, the residual zodiacal light has been the dominant source of uncertainty. The inner solar system is filled with dust that scatters sunlight from every direction, and modeling this contribution precisely enough to subtract it from a measurement 1,000 times fainter is technically challenging. Different research teams have produced estimates of the cosmic optical background that sometimes disagree by factors of 2 or more, with the disagreement often tracing back to how the zodiacal model was constructed. The experience you've most likely had of lying in a dark room and watching the darkness gradually thin as your eyes adapt captures something true about this whole layer of the problem. What we perceive as darkness is always relative to the sensitivity of our detector at the moment of measurement. A fully dark adapted eye perceives the night sky as dark, with bright stars scattered on a black ground. A sensitive camera on a long exposure reveals the airglow rippling across the background. An instrument calibrated to much fainter levels would find the zodiacal glow distributed across the sky, and a measurement that carefully removes all local contributions would find the cosmic optical background, the faint collective glow of all the galaxies that have ever shone. The darkroom experience has a specific time dimension that the sky measurement does not. Eyes adapt over roughly 20 to 30 minutes and reach their maximum sensitivity after that plateau. They do not keep getting more sensitive indefinitely. The sky, however, continues to reveal new layers of background as the sensitivity of the measurement instrument improves. There is no saturation point at which the measurement has found all the background there is. Each improvement in instrument sensitivity, or each improvement in background subtraction, reveals fainter sources that were previously masked. The history of measuring sky brightness is a history of finding that what seemed like the sky's floor was not the floor, and that there was something fainter underneath. The cosmic optical background is not necessarily the final floor either. Below it sits the contribution from light that was emitted by stars and then reprocessed, from faint sources that no telescope has yet resolved, from phenomena not yet fully characterized. Each layer of the background is real. Each represents light arriving at this point in space from some source somewhere in the observable universe. What the true cosmic background measures, and what instrument was positioned well enough to make the first convincing direct measurement of it, requires a vantage point that no observatory on or near Earth could provide. The only way to weigh the true darkness is to take the measurement from somewhere far enough from everything local that the local contributions finally fall below the signal being sought. A spacecraft was launched in January of 2006 with a single primary destination, Pluto. The New Horizons probe passed through Pluto's system in July of 2015, returning the first close-up images of that distant world and its moons, and then continued outward. By 2021, it was approximately 55 astronomical units from the Sun, roughly 55 times the Earth-Sun distance, well beyond the orbit of Neptune, and well beyond the main concentration of interplanetary dust that produces the zodiacal light. Nobody designed New Horizons to measure the darkness of the universe, but by the time it was in the outer solar system, with its sensitive long-range camera still operational and pointed at the sky, it had accidentally positioned itself as the best available instrument for exactly that measurement. It was past the corridor. The hallway light was finally far enough behind it. The hallway light problem is straightforward to describe. If you want to measure how dark a particular room really is in isolation, you cannot do it by standing in the doorway with the hall lights on behind you. The light spilling in from the corridor contributes to what your detector sees. You need to go inside the room, close the door, and then measure. In the context of the cosmic optical background, the zodiacal light is the hallway lamp. Every measurement made from Earth orbit, even from space telescopes that have eliminated the atmospheric airglow, is still bathed in sunlight, scattered off interplanetary dust. The inner solar system is filled with this dust, and the light it scatters is orders of magnitude brighter than the cosmic signal being sought. Modeling it and subtracting it introduces uncertainties that dominate the measurement. The only clean solution is to go outside the main dust concentration to the outer solar system, where the density of interplanetary dust has thinned enough that its contribution is manageable. New Horizons at 55 astronomical units had not eliminated the zodiacal contribution, but had reduced it dramatically. The dust density in the outer solar system falls roughly as the inverse square of the distance from the Sun, and at 55 times the Earth-Sun distance, the scattered sunlight from that dust is about 3,000 times fainter than it is in Earth's neighborhood. This placed the zodiacal contribution below the level of the cosmic optical background for the first time in any measurement, or close enough to that level that the uncertainty in the zodiacal model was no longer the dominant term in the error budget. The measurement of what remained after removing models of the zodiacal contribution, the diffuse galactic light from our own Milky Way, and the contributions of all individually resolved stars and galaxies in the field, was the cosmic optical background. Todd Lauer at the U.S. National Optical Infrared Astronomy Research Laboratory, along with colleagues from multiple institutions, published a measurement of this background in 2021 using New Horizons images taken with the Long-Range Reconnaissance Imager. Their results suggested a cosmic optical background roughly twice as bright as what would be expected from the population of galaxies that Deep Telescope surveys, including images from the Hubble Space Telescope, have cataloged. The initial headline was that there was more light in the universe than known galaxies could account for. The excess, if real, would require either a population of very faint, as yet unresolved galaxies spread through the cosmos, or some diffuse source of emission not associated with individual galaxies, or some systematic error in the measurement. The community's response to the 2021 result was immediate and careful. The zodiacal light subtraction, even at 55 astronomical units, required modeling. The outer solar system is not dust-free, only less dusty. A cloud of material at the outer edges of the solar system, known as the Kuiper belt, from which comets emerge, contributes some scattered light. If the zodiacal and Kuiper belt light was modeled slightly incorrectly, even a small residual could add significantly to the measured background. Follow-up analyses published in subsequent years, applying more detailed models of the interplanetary and interstellar dust scattering, found that the excess was reduced when the zodiacal model was improved. The most recent careful analyses find a cosmic optical background that is consistent within the uncertainties with what known galaxies are expected to produce, though the debate has not fully closed, and some analyses still find a modest excess above expectations. What the measurement establishes, regardless of where the ongoing debate about the exact level settles, is that the cosmic optical background is real, measurable, and has a specific finite value. Even in the outer solar system, after removing all identifiable sources of local light, there is a diffuse glow that comes from every direction equally, faint but definitively non-zero, produced by the accumulated light of all the galaxies that have ever shone throughout the observable universe and whose photons have had time to reach this point in space. This glow is the Olbers prediction, realized. It is the sum of all the stellar light that has been produced since the first stars ignited, integrated across the observable volume, arriving here from every direction simultaneously. It is just not bright enough to see. The ratio between this measured cosmic optical background and the brightness Olbers' paradox demands is approximately 10 trillion. The measured value is roughly 2 to 3 nanowatts per square meter per steradian in optical wavelengths. The Olbers' bright sky would be on the order of tens of millions of watts per square meter per steradian. The ratio between these numbers is the quantity that the finite age resolution of the paradox must account for, and it does, as the analysis that connects the age of the universe, the history of star formation, and the observable volume into a self-consistent prediction. There is a deeper point about what the New Horizons measurement is detecting. Each photon in the cosmic optical background represents starlight that left some galaxy at some point in the observable universe's history and has traveled, possibly for billions of years, to this particular location in space at this particular moment. The background is not a statistical average or a theoretical construct. It is the actual cumulative flux of real photons from real sources arriving at this location right now, each carrying a specific history of travel through an expanding universe. Some of those photons started their journey when the universe was a few 100 million years old, from the first generation of metal-poor galaxies. Some left galaxies that no longer exist, having merged or transformed in the intervening time. The aggregate of all of them, arriving from every direction at the level New Horizons measured, is the observational reality behind the theoretical resolution of the paradox. The cosmic optical background is one layer of the invisible sky. There are others. The cosmic infrared background, produced by starlight reprocessed by dust in distant galaxies and emitted as thermal infrared radiation, carries as much energy as the optical background or more. The cosmic X-ray background, produced by accreting black holes and hot intergalactic gas, fills the sky at X-ray wavelengths. The cosmic neutrino background fills every cubic centimeter of space with ancient particles from the first second of the universe's history. Each of these backgrounds represents the universe radiating in a different band, and each adds to the total energy flux passing through any point in space, most of it invisible to any biological detector. The optical layer, now measured from the edge of the solar system, turns out to have the precise brightness implied by a universe of the age, star-forming history, and observable volume that independent measurements establish from completely different evidence. The number fits. The paradox is closed in the optical band. But the sky that is full in every other wavelength, the infrared from dusty galaxies, the X-rays from black holes, the neutrinos from the Big Bang itself, is a sky whose contents we are only partially designed to perceive, and the perceptual gap between what is there and what we register is the subject that closes this entire journey. Put yourself in a room. The room is quiet, or seems to be. No voices, no machines, nothing you recognize as sound. But point a microphone sensitive to very low frequencies at any wall, and it will pick up vibrations from traffic on a road far away, from wind against the structure of the building, from seismic tremors passing through the ground. Point it at a higher frequency range and it picks up the ultrasound that bats navigate by, the communication signals of insects beyond human hearing. The room is full of sound. The perception of silence is a report about the ear, not about the air. The sky is the same inventory problem, scaled by many orders of magnitude. At optical wavelengths, it appears dark between the stars. At microwave wavelengths, it is uniformly bright with the cosmic microwave background. At infrared wavelengths, a background of starlight processed through dust in distant galaxies fills every direction. At X-ray wavelengths, the integrated emission of millions of accreting black holes and hot clusters of gas produces a background that varies across the sky in a specific pattern. At gamma-ray wavelengths, there is a diffuse background from blazars and other high-energy sources. And at a level of abundance that dwarfs all of these, the sky is filled with relic particles from the first second of the universe's history that carry information from an era no photon can ever access, particles that pass through the entire Earth as if it were not there, and which we have never directly detected as a cosmic background, even though theory predicts their density to greater precision than almost any other quantity in cosmology. These are the cosmic background neutrinos, the relic of the thermal bath that existed 1 second after the Big Bang. The early universe at that moment was too hot for protons and neutrons to have formed, too dense for any particle to travel far before interacting. Neutrinos were in thermal equilibrium with everything else, their density and energy distribution set by the temperature of the plasma. At roughly 1 second of cosmic age, the temperature had fallen far enough that neutrinos stopped interacting frequently enough to maintain that equilibrium. They decoupled. From that moment, they have been streaming freely through space, their density preserved by the expansion of the universe, their energies redshifted in proportion to how much the universe has expanded since decoupling. The universe has expanded by a factor of roughly 1 billion since the neutrinos decoupled, and their energy has been reduced by the same factor. They now move at speeds close to the speed of light if they are nearly massless, or somewhat more slowly if they have significant mass, and they fill every cubic centimeter of space throughout the observable universe at a density of approximately 336 particles per cubic centimeter. 336 relic neutrinos per cubic centimeter. The air in a room contains roughly 25 million trillion molecules per cubic centimeter. The relic neutrinos, at their density, are extraordinarily sparse compared to ordinary matter. But every cubic centimeter of space contains them, and they have been there since the universe was 1 second old. The cubic centimeters of the body listening to this, all 66,000 of them by rough approximation, contain in total on the order of 22 million relic neutrinos at any given moment, passing through without interacting, without being stopped, without leaving any detectable trace in any biological tissue or any current detector. The reason they have not been directly detected as a background is the combination of their low energy and their inherently weak interactions. Solar neutrinos, produced by nuclear reactions in the sun's core, arrive at Earth with energies on the order of millions of electron volts, and even at those energies they interact so rarely with matter that most of them pass through the entire Earth without touching a single atom. Relic neutrinos have been redshifted to energies roughly 1 trillion times lower than solar neutrinos. Their interaction cross-section with matter at those energies is so small that the probability of one relic neutrino interacting with a human body over a human lifetime is negligibly small. A detector sensitive to a single such interaction would need to contain an enormous amount of target material and be shielded from all other sources of signal with extraordinary care. The P. Ptolemy experiment, based at Princeton, has been working toward exactly this goal, using the specific endpoint energy of tritium beta decay as a potential probe sensitive to the energy scale of relic neutrinos. No definitive detection has been made yet. The CMB decoupled from matter roughly 380,000 years after the Big Bang. The relic neutrinos decoupled 1 second after the Big Bang. The information they carry is 380,000 years older than the CMB, from a moment when the universe was 1 billion degrees rather than 3,000. If they are ever detected as a background, they will provide a direct measurement of the state of the universe at an epoch otherwise accessible only through indirect inference. The CMB, which currently provides the oldest direct snapshot of the universe, represents the state of things after almost 400,000 years of evolution from the beginning. The relic neutrino background would represent the state of things at 1 second. Beyond neutrinos, there is the question of gravitational waves from the earliest moments of the universe. If an epoch of rapid exponential expansion called inflation occurred in the first tiny fraction of a second, it would have produced a stochastic background of gravitational waves, ripples in space-time carrying energy and information from an era nothing else can reach. These primordial gravitational waves would have been redshifted by the enormous subsequent expansion of the universe, arriving today at frequencies that fall in a range accessible to future space-based gravitational wave observatories. Ground-based detectors currently operating are not sensitive at those frequencies, though pulsar timing arrays, which use millisecond pulsars as precise clocks to detect gravitational waves via timing delays, published evidence in 2023 for a stochastic gravitational wave background. Whether the signal is primordial or from more recent astrophysical processes is not yet established. The detection itself has opened a window into gravitational wave astronomy that will expand considerably in the next decade. Taking inventory of a single point in space, a point no different from the one occupied by the body lying here in the dark, the contents are these: several hundred CMB photons per cubic centimeter, arriving from every direction, carrying the thermal signature of the universe at 380,000 years, 336 relic neutrinos per cubic centimeter, carrying information from the first second, undetected by any biological or current technological means. A diffuse background of optical photons from all the galaxies that have ever shone, arriving from every direction at the level measured by New Horizons. Infrared photons from dust-processed starlight in distant galaxies. X-rays from accreting black holes at cosmological distances. Gravitational waves, if they exist at detectable levels, stretching and compressing space by amounts smaller than a proton. And dark energy, the dominant energy density of the universe, uniform throughout all of space, exerting its influence on the expansion without any known mechanism for direct interaction with matter. None of this registers in the eye. None of it registers in any sensory apparatus the body carries. The darkness of the night sky is not a property of the space the sky represents. It is a measurement of the frequency range between 380 and 700 nanometers, made by a detector that evolved in a specific thermal environment around a specific star, over a span of time during which that was the only radiation in the environment worth building a detector for. The sky appears dark. The space it represents is not dark in any physical sense. Every point in it is permeated by ancient particles and ancient photons and ancient waves, most of them carrying information from eras that no other signal can reach, all of them undetected by any biological system that has ever existed. What it means to call this sky dark, and whether the darkness is a stable condition or is quietly shifting under forces still in motion, is the question the last pieces of this have to address. The universe is not simply expanding. It is expanding at a rate that is increasing with time. The space between galaxy clusters is growing not at a steady pace, the way a ball rolling along flat ground moves, but at an accelerating pace, the way a ball rolling down a steepening slope moves. This is not what anyone expected to find when, in the late 1990s, two independent teams of astronomers began measuring the distances to Type Ia supernovae at high redshift. Their purpose was to measure the deceleration of the expansion, which standard models of the time predicted should be occurring as gravity gradually slowed the outward motion from the Big Bang. What they found instead was that distant supernovae were fainter than they should be if the expansion were constant or decelerating. The universe was not slowing down, it was speeding up. Saul Perlmutter, leading the Supernova Cosmology Project, and Brian Schmidt and Adam Rees, leading the High Z Supernova Search Team, published results in 1998 and 1999 that independently confirmed the same conclusion. The 2011 Nobel Prize in Physics recognized this discovery. What drives the acceleration is still not understood. It is called dark energy, a term that marks a genuine limit in understanding rather than a description. Dark energy makes up approximately 68% of the total energy content of the universe. It is uniform throughout space, does not clump under gravity, and does not dilute as the universe expands the way matter and radiation do. Its effect on space is to produce a repulsive pressure that increasingly dominates the dynamics of the expansion as the dilution of matter and radiation over time leaves dark energy as the dominant term in the equations. The closest mathematical equivalent is a cosmological constant, a term that Albert Einstein added to and then removed from his equations, apparently prematurely. The accelerating expansion has a direct consequence for the future darkness of the sky. In a universe where the expansion accelerates without limit, there is a boundary beyond which no light emitted today will ever reach any future observer here. This boundary exists because space between here and the distant regions is expanding faster than light can cross it. A photon emitted toward us today from a source beyond this boundary will be chasing a target that is receding faster than it can move. The photon will never close the gap. This boundary is the cosmological event horizon, and it sits at a comoving distance of roughly 16 billion light-years from us in the current era. Light emitted today from inside that boundary will eventually reach us. Light emitted today from outside it will not. Regardless of how much time passes, the observable universe extends to roughly 46 billion comoving light-years. containing the entirety of the volume from which any light has had time to arrive since the Big Bang. The cosmological event horizon, at 16 billion moving light-years, is the boundary for light emitted now. Galaxies currently inside the observable universe, but outside the cosmological event horizon, can still be seen because their light was emitted in the past, when they were closer to us and has already been traveling toward us long enough to arrive. But any light those galaxies emit from this point forward will never reach us. We are seeing them as they were. We will not be able to see them as they become. As time passes, the expansion pushes more and more galaxies beyond this horizon. Galaxies that are currently observable because their past emitted light is still arriving will eventually fall silent as their newest photons are lost. The observable sky becomes progressively emptier, not in any short time frame perceptible to human civilization, but over billions of years of continued expansion. The specific rate at which galaxies are being lost over the horizon is not zero now, but the effect accumulates slowly over cosmological timescales. In the very long future, on timescales of tens to hundreds of billions of years, the Milky Way and Andromeda will have long since merged into a single structure, and that merged galaxy will sit essentially alone in the observable universe, with the rest of the cosmic galaxy population having receded beyond any recoverable distance. The CMB is also on a trajectory toward undetectability, independent of the horizon question. The expansion continues to stretch the CMB photons to longer and longer wavelengths. At the current temperature of 2.725 degrees above absolute zero, the CMB is already in the microwave range, invisible to all biological detectors. As the universe expands further, its temperature will fall. The CMB will shift from microwave wavelengths to radio wavelengths, and its energy density will dilute further. On timescales of trillions of years, the CMB becomes so cold and its photons so long in wavelength that it becomes effectively undetectable by any instrument operating at the energy scales of ordinary matter. The 336 relic neutrinos per cubic centimeter will remain, their density declining slowly as the volume of the universe grows, their interaction cross-section remaining negligible. The relic neutrino background will persist longer than any electromagnetic signal, but without any foreseeable means of direct detection, it will be a presence that cannot be read. What the accelerating expansion is doing to Olbers' paradox is making it more resolved, not less. The dark sky exists because the universe is young and most shells of stars have not contributed their light. As time passes, more shells contribute, which should, in principle, be brightening the sky. But the accelerating expansion is simultaneously removing shells, pushing galaxies over the horizon at a rate that increasingly competes with the inward flow of new light from previously unreachable sources. The net effect, over the very long term, is that the number of contributing shells does not grow indefinitely. It reaches a ceiling and then, as the accelerating expansion wins, begins to decline. The dark sky of the far future will be darker than the dark sky of today. This is the direction the universe is moving, not toward the Olbers' bright sky that the static, eternal model demanded, but away from it, driven by an energy of unknown nature that fills all of space and grows in influence as matter and radiation dilute away. If the sky is getting darker, if light has always been the exception and darkness the direction, the question left is what the darkness itself amounts to, and whether the universe heading toward it is heading somewhere meaningful or simply running down. Pick a point at random inside the observable universe, not near any particular galaxy, not guided by any preference for where life happens to exist, just a point chosen by coordinates distributed uniformly through the entire volume. The overwhelming probability is that the point is in intergalactic space, far from any galaxy, at a location where the nearest star is millions of light-years away. The observable universe has a volume on the order of 4 times 10 to the 80th cubic meters. The total volume occupied by all the stars within it is a small fraction of that. Stars are dense objects, but there are not enough of them, spread over a large enough volume, to constitute anything other than occasional exceptions to the rule of empty space. The probability that a randomly chosen point in the observable universe is inside a star is on the order of 1 in 10 to the 24th power. The probability that such a point receives radiation at anywhere near stellar surface intensity is higher, because light travels outward from stars, but it is still extremely low compared to the volume that receives essentially no starlight worth measuring. The distribution of light in the universe is not a smooth field. It is a field of extreme concentration at specific tiny locations, surrounded by vast regions of near-zero intensity. A photon emitted by the sun at the sun's luminosity follows an inverse square drop-off as it travels outward. At Earth's distance, the sun delivers about 1400 watts per square meter. At the distance of the nearest other star, about 4 light-years, the sun's output has dropped by a factor of roughly 260,000 compared to Earth's position. At the edge of our galaxy, tens of thousands of light-years away, the sun's contribution to any local radiation field is negligible by any measure. The light that stars produce is real, intense at the source, and practically absent at nearly every other location in the universe. This is not just a statement about the present moment. It is a statement about the future trajectory of the universe, carried to its conclusion by the physics that makes stars possible and impossible. Stars are not a permanent feature of the cosmos. They are a phase, driven by the finite supply of hydrogen that can be compressed into nuclear reactions under gravitational pressure. The most massive stars burn through their fuel in millions of years. The sun will exhaust its core hydrogen in about 5 billion years. The smallest stars, the red dwarfs that make up the majority of stars by count, burn so slowly that they can persist for 10 to 100 trillion years. After them, no new stars can form in the conventional sense, because the universe's supply of fuel that can be assembled into star-forming conditions is being progressively depleted. On a timescale of roughly 100 trillion years, the last red dwarf will have faded. What remains will be stellar remnants, white dwarfs, neutron stars, and black holes, none of which produce significant light. White dwarfs, the cooling embers of sun-like stars, will radiate heat slowly into the increasingly cold universe, cooling over timescales of many quadrillions of years until they match the background temperature. Black holes, which consume matter that falls into them, will eventually lose mass through a quantum process known as Hawking radiation, radiating energy at a temperature inversely proportional to their mass, ultimately evaporating completely on timescales that make even the age of the universe seem brief. The most massive black holes will take on the order of 10 to the 83rd to 10 to the 106th years to evaporate. After they are gone, the universe will be in a state of approximate thermal equilibrium, every point in space at the same vanishingly small temperature, with no concentration of energy anywhere that could drive any process. This endpoint is called the heat death of the universe, or maximum entropy. It is the state where the temperature everywhere is the same, and therefore no energy can flow from one place to another to do work or produce light. Nothing in the known physics of the universe prevents this endpoint. The accelerating expansion ensures that matter and radiation become increasingly dilute. The stellar burning of hydrogen into heavier elements is not reversible on cosmological timescales. The Hawking evaporation of black holes is the last significant energy release. After it is complete, the universe will be dark in every band, at every scale, uniformly, permanently, and with no mechanism for the darkness to ever reverse. The fraction of cosmic time during which the universe contains any working stars is itself a remarkable number to hold. If the universe runs for 10 to the 106th years before the last black hole evaporates, and the era of conventional stellar burning lasts roughly 100 trillion years, that era occupies approximately the first one, followed by 85 zeros of the total time span. The fraction is so small, it effectively has no name in everyday language. In a timeline that long, 100 trillion years of starlight is a thin line at the very beginning, thinner relative to the total than a single frame of a film that runs for billions of years. The darkness before and after is not empty waiting. It is the timeline, and the light is the briefest of annotations. The image that fits this is a page of paper, not a drawing that covers the page with content, but a page on which a few sparse marks have been made, separated by vast regions of unmarked white. The marks are the stars and galaxies, each one a concentration of nuclear reactions burning through a finite supply of hydrogen. Each one temporary, each one surrounded on all sides by expanses of page that the marks do not touch. The page itself, the default surface, is the dark. The marks are the departures from it. The question that the universe poses is not why there is so much of the page unmarked, but why there are marks at all, and for how long. In this framing, Olbers asked his question from the inside of one of the marks. He looked outward from a star, surrounded by other stars, and asked why the gaps between the marks were not also bright. The answer required understanding not just the marks but the page, what the universe defaults to, what the duration of the marks is compared to the duration of the page, and what mechanism produces marks in the first place, rather than leaving everything uniformly blank. The answer to all of these connects to the initial conditions of the universe, the specific values of the fundamental constants, the specific amount of hydrogen available for star formation, and the specific duration of the era in which those initial conditions produce the configuration we find ourselves in. None of those specific values were required by any law that has been discovered. They are what happened to be the case. The universe could have had less hydrogen, or different constants, or a different initial temperature profile, and the era of marks would have been shorter or longer or would not have happened at all. The page might have stayed blank. What it means to be inside one of the marks, looking outward at the page, and what that position implies about the body that finds itself here in the dark, is what the remaining thread has to address. The darkness surrounding the marks is not the universe failing to produce something. It is the universe at rest, in the state it will return to when the marks fade, and the state it will remain in without interruption for every duration that follows. Place an object in the emptiest location you can find in the universe, a point in the void between galaxy clusters, hundreds of millions of light years from the nearest significant concentration of matter. Let it radiate heat freely into the surrounding space. It will cool. It will keep cooling. And then it will stop cooling, not because the cooling mechanism has failed, but because the surrounding space is not at zero temperature. The darkness around it has a temperature, and no object sitting inside that darkness can fall below it. That temperature is 2.725 degrees above absolute zero, the temperature of the cosmic microwave background. In the current era of the universe, this is the floor. The warmest an object gets in deep space without a local source of energy is much higher, set by the nearest stars or galaxies, and the coldest it can get is this, set by the radiation field of the early universe that permeates all of space. The darkness has a thermal lower bound, and it is not zero. The mechanism is straightforward. Any object radiates heat, emitting photons at a rate and wavelength set by its temperature. Any object also absorbs radiation from its environment. In equilibrium, the absorbed and emitted rates match, and the temperature stabilizes. An object in a room comes to equilibrium with the walls and air of the room. An object in deep space, far from any local source of heat, comes to equilibrium with the only radiation field present in every direction equally, the CMB. The CMB photons strike the object from every direction, depositing a small but non-zero amount of energy with each arrival. For the object to cool below 2.725 degrees, it would need to radiate more than it absorbs. But once it reaches CMB temperature, the emission and absorption balance exactly. The darkness is providing heat, faintly but continuously, preventing any further cooling. 2.725 degrees above absolute zero is close to absolute zero, but not at it. In terms of temperature scales familiar from daily life, absolute zero is -273 degrees Celsius. The CMB temperature is negative 270 degrees Celsius and 3/4. The difference between the CMB temperature and absolute zero is about as far above zero as the coldest liquids used in laboratory cryogenics. Liquid helium, the coldest substance routinely handled in experimental physics, boils at about 4 degrees above absolute zero. The CMB temperature is below even that. The darkness of deep space is colder than liquid helium, but not as cold as the experiments that probe the quantum behavior of matter at temperatures within hundredths or thousandths of a degree above absolute zero. Somewhere in the range of the coldest things humans have deliberately made is where the darkness of the universe's radiation field sits as a floor. The darkness around you right now is not at 2.725 degrees. The room, the air, the walls, and the body all emit and absorb radiation at temperatures much higher, and the CMB contribution to the room's radiation field is completely swamped by all of it. But the CMB photons are present in the room, threaded through every cubic centimeter, adding their faint contribution to the total radiation field. If every local source of heat could be removed, if the room and everything in it could be cooled to the point where only the cosmic background remained, that background would hold the temperature at 2.725 degrees and refuse to let it fall further. The darkness carries its own warmth, too faint to feel, too real to dismiss. Below the CMB temperature, quantum mechanics introduces a further set of reasons why empty space is not empty. Classical physics describes a vacuum as a region containing nothing, no matter, no energy, no fields of any kind. Quantum mechanics does not permit this. The uncertainty principle forbids any system from having both a precisely defined position and a precisely defined momentum simultaneously, and an equivalent principle applies to energy. A vacuum cannot have precisely zero energy at precisely a defined moment. It must fluctuate randomly and continuously, with the fluctuations averaging out over time but never being exactly zero at any instant. These fluctuations are real physical phenomena, not mathematical artifacts. They produce measurable forces. The most direct demonstration of this is the Casimir effect. Take two uncharged, flat metal plates and place them very close together in a vacuum, with no other charges or fields nearby. The classical prediction is that nothing should happen, because there is no charge or current to create a force between neutral objects. The quantum prediction is that the plates will attract each other, because the vacuum between them supports a smaller range of quantum fluctuation modes than the vacuum outside them. The energy of the vacuum between the plates is slightly lower than the energy of the vacuum on the outside, and the plates are pushed together by the difference, like two objects being pressed together by a pressure difference. This force has been measured in laboratory experiments to high precision, and it matches the quantum prediction. The Casimir force is a force generated by nothing, in the literal sense of a force that arises from the properties of a vacuum containing no particles. The same vacuum fluctuations appear to an accelerating observer as a thermal background. An observer moving through a vacuum at constant acceleration would detect radiation at a temperature proportional to that acceleration, a phenomenon known as the Unruh effect. For any acceleration achievable in practice, this temperature is so small as to be unmeasurable, but the theoretical framework is well established and has been confirmed through the mathematical relationship it shares with Hawking radiation from black holes. The key implication is that temperature is not an absolute property of space, but a property of the relationship between a physical system and the observer measuring it. Even in what would be considered a perfect vacuum by any practical standard, the quantum structure of space introduces a thermal character that depends on the state of motion. In a universe driven by a cosmological constant, which is one way of describing the dark energy responsible for the accelerating expansion, there is an additional temperature associated with the cosmological event horizon itself. This temperature, known as the Gibbons-Hawking temperature, is on the order of 10 to the negative 30 degrees above absolute zero, incomprehensibly close to zero, but not at it. This is not the CMB temperature and not the Unruh temperature, but a distinct quantum effect arising from the existence of a cosmological horizon analogous to the Hawking temperature of a black hole in the very far future. After the CMB has redshifted to wavelengths so long as to be undetectable, after all stars and black holes have gone dark, this Gibbons-Hawking temperature would be the last thermal floor of the universe, and even that is above absolute zero. The darkness that surrounds everything is layered in exactly the way the light was layered. It has a CMB temperature floor. It has quantum vacuum fluctuations. It has, in the current era, the small contributions of relic neutrinos and the diffuse electromagnetic backgrounds at every wavelength. It has the Gibbons-Hawking temperature of the cosmological horizon. None of these layers add up to warmth in any biological sense. All of them add up to a darkness that is structured, that has properties, that is not nothing. The body in the dark right now is inside all of these layers. The CMB photons pass through it. The relic neutrinos pass through it. The quantum vacuum fluctuates throughout its volume. Dark energy fills every cubic centimeter of it, as it fills every cubic centimeter of everything. The darkness you perceive while lying here is one reading of a space that is, on careful examination, full. If the darkness is full, and the eye is only catching a narrow slice of what is present, then calling the sky dark says more about the structure of the eye than about the structure of the sky. That is the turn the question has been building toward from the beginning. The electromagnetic spectrum runs from radio waves with wavelengths of kilometers, long enough to pass through buildings and mountainsides without noticing them, down to gamma rays with wavelengths shorter than the diameter of an atomic nucleus. The full span of this spectrum, measured on a logarithmic scale the way frequencies are naturally compared, covers roughly 25 octaves of wavelength. The portion of it that human eyes respond to spans from 380 to 700 nanometers, a range of wavelengths spanning less than 1 octave. As a fraction of the electromagnetic spectrum's total measurable extent, the human visual range occupies something close to 0.004%. The other 99.996% of the spectrum, carrying energy in forms that fill the universe in every direction, passes through the eye without producing any signal whatsoever. When you look at the dark patch of sky between two stars and see nothing there, your visual system is not detecting the absence of anything. It is detecting the absence of photons in the 380 to 700 nanometer range. Everything else that is present in that patch of sky, the CMB photons at millimeter wavelengths, the relic neutrinos at thermal energies below a millielectron volt, the cosmic infrared background from distant dusty galaxies, the X-ray background from accreting black holes, the quantum vacuum fluctuations, all of it is present and none of it is reporting to the visual system. What the eye registers as empty is a space full of signals that the eye is not built to receive. The darkness is not in the universe, it is in the receiver. This is not a trivial or abstract point. It is a statement about the relationship between sensory systems and the physical environments they evolved in. Eyes do not perceive the universe. They perceive a frequency-selected subset of the universe that corresponds to the radiation environment in which their ancestors reproduced. The sun produces a broad thermal spectrum with output peaking near 550 nanometers, and biological photoreceptors sensitive to that range would be more useful in a survival context on a sunlit planet's surface than photoreceptors sensitive to radio waves or X-rays. Natural selection optimized for the local radiation environment and the local radiation environment around a G-type star at 1 astronomical unit of distance is not the same as the radiation environment of the universe at large. Other biological systems demonstrate that the visual range is not special. Bees and many other insects detect ultraviolet light down to about 290 nanometers and use it to navigate flower patterns invisible to human eyes. Some species of pit vipers, pythons, and boa constrictors detect infrared radiation between about 714,000 nanometers through specialized pit organs, allowing them to sense the body heat of prey in complete optical darkness. Some fish navigate using the detection of electric fields. Migratory birds appear to use the polarization of light and potentially even the Earth's magnetic field for orientation. Mantis shrimp have 16 types of photoreceptor cells where humans have 3. Each of these systems samples a different slice of the physical world, and none of them is sampling the world as it is. They are all sampling the world through a filter shaped by the evolutionary pressures of a specific ecological niche. The human visual range is the filter shaped by one ecological niche on one planet around one star. That niche happened to make the narrow band between 380 and 700 nanometers useful. Outside that context, there is no physical reason to privilege that band. The CMB, which fills the universe from every direction with 400 photons per cubic centimeter, is not in a privileged part of the spectrum from any physical standpoint. It happens to fall in a range the human eye discards. The experience of darkness involves something beyond the mere absence of signal at the relevant wavelengths. The brain does not simply register no photons and produce no experience. It actively constructs the perception of darkness. In conditions of very low visual input, the visual cortex increases its sensitivity, attempts to extract patterns from random neural noise, and sometimes generates percepts without any external source, which is why prolonged exposure to genuine darkness can produce phosphene-like visual experiences even in the complete absence of light. The darkness you see is not the raw output of a photon counter reading 0. It is a constructed experience, produced by a biological system doing its best to make sense of an environment in which its signal channel has gone quiet. When the visual system goes quiet, the brain fills the gap with what it expects, which, in an evolutionarily familiar context, is the local darkness of night under a local sky, not the rich radiation background of cosmological space. A radio telescope pointed at the same dark patch of sky registers the CMB. A neutrino detector with sufficient sensitivity would, in principle, register the thermal neutrino background at 1.95 degrees above absolute zero. An X-ray telescope pointed at the dark gaps between visible stars finds a diffuse background of X-ray emission from high-energy astrophysical processes across the universe. A gravitational wave observatory, if sensitive enough, would find the stochastic gravitational wave background, potentially from early cosmic processes. In none of these instrument views is the same patch of sky dark. The darkness is an artifact of one specific detection channel, the optical one, not a property of the space being observed. The specific fraction bears repeating because it recalibrates the sense of what we know about the universe from direct observation. 0.004% of the electromagnetic spectrum is what enters the eye and constitutes all of human visual experience. Every painting ever made, every astronomical observation ever recorded on photographic plates, every image returned by optical telescopes, from Galileo's first lens to the James Webb Space Telescope's deep field images, all of this comes from 0.004% of the available electromagnetic signal. The remaining 99.996% has been largely invisible to biological observers for essentially the entire history of life on this planet, accessible only in the last few centuries, as technology extended human detection beyond the optical range. The resolution of Olbers' paradox says that the visible sky is dark primarily because the universe is young and most stellar light has not had time to arrive. This is true and correct as far as it goes, but following the question all the way to the end produces a different picture. The sky is full. It is full in the microwave range with the CMB, full in the radio range with various backgrounds, full in the X-ray range with high energy source backgrounds, full in the neutrino channel with relic particles from the first second, full in the quantum sense with vacuum fluctuations. The dark sky between the stars is the emptiest it gets in visible wavelengths, and visible wavelengths are the narrow channel through which biological vision on Earth was built to operate. One way to hold this is to imagine a listener who can only hear a single narrow frequency band, perhaps the range of a specific musical instrument. For that listener, most conversations would be inaudible, most environmental sounds would be silent, and the world would seem much quieter than it is. The listener would not be wrong about what they hear, but they would be significantly wrong about what there is to hear. The eye in its relationship to the electromagnetic spectrum is this listener, except that the eye's restricted range is a fraction of a percent of the total, not a narrow band in an otherwise complete spectrum. The question that has been running through this entire exploration, why is the sky dark, has an answer in the physics of finite age, expanding space, and the sparse distribution of stars. But held against what the sky contains, the question acquires a different shape. The sky is not particularly dark. It is full of radiation in almost every frequency. The question the physics answers is why the optical sky in particular is dark. And the answer to that more specific question includes, inseparably, the fact that the creature asking it happens to have evolved eyes. What it is like to be inside a radiation field that your sensors only partially register, and what it means to understand something you cannot perceive, is the last thing this particular thread has to say. There is a specific thing that changed for me in working through all the layers of this problem. The question arrived as a paradox. Why is the sky dark and left as something else entirely? Not an answer to the original question, but a reframing of what the question was about. The sky is dark in visible wavelengths for the reasons the physics lays out. But the experience of looking at the dark sky and asking why it is dark is an experience of looking at a system that contains the entire history of the universe and concluding that it contains nothing. That inversion is the uncomfortable part. The thing that looks most empty is the thing that is most full. The question that seems most obvious is the one that requires the most of physics to answer. And the answer, once assembled, is that the question was always about here as much as it was about there, about the structure of the eye as much as the structure of the cosmos. Pick a dark patch of sky between any two visible stars and hold it in view. It takes no instruments, no telescope, no special location. Any dark gap between any two bright points on any clear night will do. That gap looks empty. It is not. Everything this long arc of argument has been building is simultaneously present in that gap, not as an abstraction or a summary, but as actual physical information encoded in the radiation field, the particle density, and the geometry of the observable universe as seen from exactly where you are standing. The specific dimness of that patch, the fact that it is dark rather than bright, is a measurement of the age of the universe. The total brightness of the night sky between the stars is set by how long stars have been burning and how much volume they have had time to illuminate. A universe twice as old would have a visibly brighter background sky. A universe half as old would have a darker one. The level of darkness you see in that gap is not arbitrary. It corresponds to a universe that has been burning stars for approximately 13,800,000,000 years, and if you had access to the right calibrations, you could read that number off the sky the way you read time off a clock. Edward Robert Harrison showed that the calculation closes. The measured sky brightness and the measured age of the universe, derived from entirely separate observations, are consistent with each other. The darkness is a self-consistent measurement. Within that dimness, the specific wavelengths that are absent encode the speed of light. The directions that appear dark are directions where the photons from stars and galaxies are still in transit, traveling toward you at 300,000 kilometers per second, and have not yet arrived, because the combination of the universe's age and the distance involved has not given them enough time. The darkness between the stars marks the sight lines where light has not yet closed the gap. The apparent emptiness is a travel time, expressed as an absence. The slight additional dimming from the universe's expansion is also there, written in the background. The photons that have arrived from distant sources have been stretched by the expansion. losing energy in proportion to how much the universe has grown since their emission. The sky is fractionally darker than it would be in a static universe of the same age by the amount that expansion has drained from the photons already received. This is not the dominant effect, but it is present, a second measurement layered into the same patch of darkness. And then there is what the patch contains invisibly. At millimeter wavelengths, the same gap between two stars is not dark at all. It glows uniformly with the cosmic microwave background at 2.725 degrees, the remnant of the early universe's plasma state, arriving from every direction with equal intensity. The Olbers bright sky that the geometry demanded has existed all along, shifted to wavelengths the eye discards. The paradox's prediction came true. The gap is the bright sky Olbers wanted, translated into a language the eye was not built to read. Below the CMB, the relic neutrinos pass through that gap in every direction, moving at near light speed if they are essentially massless, or somewhat more slowly if they have mass, carrying information about the state of the universe at 1 second after the beginning. 336 of them per cubic centimeter, undetectable by any current instrument, present in the gap as surely as the CMB photons. And the quantum vacuum fills the gap with its fluctuations, and the dark energy fills it with its uniform density, and the gravitational wave background passes through it if it exists at detectable amplitudes. Working through all of this layer by layer, over time, there was a moment when the reversal became complete for me. The question that began this was, why the sky is dark? The answer, pulled to its full depth, is that the sky is not dark. The sky is full. The darkness is a reading that one particular biological instrument, tuned to one particular wavelength range in one particular evolutionary context, produces when it looks at a space that is carrying more information per cubic centimeter than any library ever built. The night sky between the stars is the most information-dense thing most people will ever look at without knowing it. The image that fits is a page of writing, not a page with a few sentences on it, but a page filled top to bottom and margin to margin with text in many overlapping scripts. The page looks blank because most of the scripts are in inks that human eyes do not detect. There are a few visible marks, the stars, the planets, the Milky Way band. But the page itself, the background the visible marks sit on, is not blank. It is written in CMB photons at millimeter wavelengths, in relic neutrino densities at sub-millielectron volt energies, in quantum vacuum structure, in the geometry of the observable horizon, in the age of the universe expressed as a brightness level, in the expansion rate expressed as a spectral shift. Each of these is a real inscription, physically present, carrying real information, readable in principle by instruments appropriately tuned. The body lying in the dark right now is not looking at that page from outside. It is inside the page. The radiation that fills the dark patch of sky between two stars fills this room to the same density, to the same temperature, with the same relic neutrinos per cubic centimeter. The CMB photons are not only out there between the stars, they are here, passing through the walls, the air, the body itself, at 400 per cubic centimeter in every direction simultaneously. The person who lies here and perceives darkness is lying inside the oldest radiation in the universe, inside the information that encodes the age and expansion and structure of the cosmos, inside the page that looks blank because the eye was built for a different ink. The darkness around the body is the same radiation field as the darkness between the stars, the same CMB temperature, the same relic neutrino density, the same quantum vacuum. The question that seemed to be about the sky turns out to have been a question about the space that includes this room and this body and everything that lies in any direction from any point in the observable universe. The dark sky paradox was a question about here, not just out there, what the oldest layer of that darkness is, the layer that predates every star and every galaxy, and whether it is passing through this particular room and this particular body at this particular moment is where the answer finally closes on itself. The beginning of the universe is not behind you. It is passing through you right now at 2.725 degrees above absolute zero from every direction at once. The cosmic microwave background is passing through this room. Not as a figure of speech or a way of saying that ancient events have consequences that ripple forward. As a physical fact, right now, while this sentence is being heard, photons that have been traveling since the universe was 380,000 years old are crossing every cubic centimeter of this room at the speed of light. They are passing through the walls, they are passing through the air, they are passing through the body lying here. The passage is continuous, uninterrupted, and has been ongoing since the universe first became transparent, long before this planet formed, long before the solar system formed, long before any star in our galaxy was born. The room is not where the ancient light is visiting. The room is inside the ancient light, the way a fish is inside the water, the way the planet is inside the sun's continuous radiation, except that this particular radiation is far older than the sun and comes from every direction simultaneously with no variation in intensity. This is not the same as saying the room is glowing. The CMB at 2.725 degrees above absolute zero carries far too little energy per photon to produce any sensation of warmth or light in any biological detector. The photons pass through tissue, through bone, through every material in the room, interacting with matter so rarely that not one of the billions of CMB photons crossing the body at any given moment will leave any measurable imprint on any molecule. The passage is invisible, unfelt, undetectable by any sense the body carries, and it is real. The faint thermal radiation of the beginning of the universe is physically present in the body, not as a historical fact but as a current condition. 2.725 degrees is not zero. It is a real temperature, carried by real photons, arriving from real directions. The slight warmth that began 13,800,000,000 years ago, reduced by expansion from 3,000 degrees to something just barely above absolute zero, is crossing the body right now, from every direction, with perfect uniformity. The photons that are crossing this room tonight were already in transit before the Earth was formed. They have been traveling for longer than any geological record, longer than the oldest rock, longer than the oldest star in this galaxy. Each of them was produced at a specific moment when the universe made the transition from opaque to transparent, when electrons combined with protons throughout all of space at essentially the same cosmic time, and each of them has been moving without interruption from that moment to this one, carrying the thermal signature of that transition as a wavelength, as an energy, as a direction. They carry no information about anything that has happened since then. Stars formed and died, and the CMB photons kept traveling. Galaxies assembled. The solar system formed, the Earth cooled, life began, species emerged and vanished, and the CMB photons kept traveling. Every night of every human life that has ever been lived, the CMB was crossing the room where the living happened, undetected, unnoticed, consistent. Sleep does not interrupt it. The photons do not wait for consciousness. They cross the room in the same way when the body is awake and when it is asleep, when the eyes are open and when they are closed, when the mind is following an argument and when it has released the argument and drifted into something else. Closing the eyes does not change the radiation field. Lowering awareness does not change the physics. The ancient light that is here now will be here when the body wakes, will be here in the morning when the sun rises into a sky that looks blue from inside the atmosphere, will be here at noon when the sun is bright and the CMB is still present, mixed into the room's radiation background, too faint to matter in practical terms and too real to dismiss. The question that opened all of this was simple. Why is space so dark when the stars are so bright? The answer involved the age of the universe, the speed of light, the expansion and the redshift, the history of stellar populations, the structure of the observable horizon, the nature of biological vision, the temperature of the quantum vacuum, and the existence of a radiation field so old and so faint that no human sense can register it? The answer is also simple, in the end. The sky is not dark. The sky between the stars is full of photons from the beginning of the universe, present in every direction at 2.725 degrees, invisible to eyes evolved in a very different radiation environment. The darkness is a description of one narrow sensory channel. The reality, the physical reality of what is present in every direction from every point, is a universe full of ancient light still traveling, still crossing every room in which any person has ever stood and looked up and wondered about the dark. There is something in that worth resting in. Not because it resolves anything about how to live, not because it makes the darkness less dark in any practical sense, but because the question this started with turned out to be a question about something much larger than a dark sky, and the answer turned out to be present here, in this room, passing through the body without ceremony or announcement, the way all the most fundamental facts about the universe are present at every location simultaneously, without requiring any special effort to find them. The beginning did not stay at the beginning. It is here. The universe is crossing you right now, in every direction, at the speed of light, from 380,000 years after it began. You are the most recent thing it has encountered on that journey, and you will not be the last. It crossed this region of space before any of this was here, and will cross it long after. But for this particular moment, it crosses a body that went looking for it, that followed the question far enough to find where the ancient light had gone, and that is lying here now, inside the answer. The room is full of the beginning. The darkness around you is carrying 13 billion years of travel. Whatever sleep comes, the light will still be crossing here when it does, and it will still be crossing here when you wake. Thank you for spending this time with something as old as the universe and as small as a question about the dark. Whatever the night brings, you are resting inside the oldest warmth there is. Let it hold you. Sleep well,